compliance. Feel better, you start doing it, and that brings the symptom. So common causes of corneal blindness, of course this is normal. What happens, trauma, injury or infection leads to this disease, and we have developed this in vitro model how to study that, because we cannot use all the time animals and humans. So this is the model which is our use. So we have, this is the transparent cornea. What we have done, we have taken these cell type from the cornea, stromal cell type, they call keratinocytes, and when after the injury or any infection happens, you see they change their properties, they differentiate into the fibroblast, and then eventually to myofibroblast to do the wound repair. And so what is here with the red color stain is the smooth muscle-acting protein, which is a biomarker for the fibrotic response. And so this is why you don't see it. That tells you this is a clear cornea. And when you see this means injury has happened, the wound healing process started. And when this happens, either wound healing is at the peak, or it just, is staying, or cornea become opaque, or your vision is lost. How the fibrosis happens, and these are the factors and pathways. Do you think anyone can study that? And this is just one. There will be a lot more of those, of course not, right? So you have to develop some approach. So what I did, I developed a very simple approach, just studying them, grouping them, classifying them, and again, my chemistry knowledge helped. Biologists just get stuck with that. I said no. We need to classify. So we did classify it, and just he said, let's see what is the thing. And being a chemist, I still like this flow diagrams. What you do in metallurgy is in chemistry. So I said, no, what happened? This is keratinocyte. After injury, there is activated all these factors which we showed in the previous slide. Activate this fibroblast, and one of these factors, TGF beta, differentiate these cells into myofibroblast. And this is the cell which are supposed to be there when after the injury to do the repair. And after repair, they're supposed to die through apoptosis, which is a normal dying process of the cell, and cornea becomes clear. So your vision does not get affected. However, many of these times, if they stay here, they keep producing these irregular ECM proteins, and that's how the fibrosis happens or your vision loss happens. So this actually, appeals to all the new students which come in my lab, and they feel like they can do it. If I show them the previous slide, they will run away. They will not show back again in the lab. So these are our tools which we use to study all this process. And this is the models which we have developed. So I have a privilege of being very few basic scientists, including in the cornea field. Before that, in 1993, most of the people were clinicians, they don't know. So it helped me build a relationship, partnership with clinicians and with the PhD. So that's how we were able to develop many of these models. And this is the rabbit model. Rabbit cornea is very similar to human in the terms of structure, function, and size. So that's why we use it. And rabbit are easy to handle. They are very, loving animals. So you pet them, they recognize you. So, and that's what we use them. And of course, mouse is not a good translational model, but it's very important for study the gene function. So we use them, we develop them. And then eventually we want to take a human, so we have to have a large animal model. So we developed a dog model in 2016. But this is the first and last study which we did with the dog. I had so much trouble with animal PETA activists, you won't believe it. So I started working on that, and we developing the porcine model, which is a pig model, which will be equal to the, not equal to the dog, but it will be better. At least I will have less trouble in the lab. So what we have classified, now we have to find a therapeutic target and strategy, how to develop that. So trauma, corneal wound healing starts, which I show you with a complex slide and a simple slide. And then what process drives that simple thing. So we classified in the 5 different processes. First is the keratinocyte apoptosis in 1990s when we went to US, and apoptosis was the peak. They got the Nobel Prize. Every paper you read in the science is the apoptosis. So of course I wanted to do also. So we did it, tested it in the controlling this corneal fibrosis. And then next is proliferation and then keratinocyte differentiation, which is TGF-beta mediated, and then ECM and NLP modification. And then epigenetic regulation, I have privilege and honor of that we, the first group in the world to show epigenetic modification and effect of modifier agent to treat the corneal disease. So that's what we did it. At that time it was unknown. So what we have done, we try to use all these inhibitor activators for the apoptosis to treat the corneal blindness. Of course, didn't work. Everything failed. We tried. So then we moved to the second one where we blocked this keratinocyte proliferation. So mitomycin C is a drug which is developed for cancer, but they didn't make enough money with cancer. It is still not approved for ophthalmology, but it is used most readily in the ophthalmology. They make all the money, company make all the money through ophthalmology, not with the treating the cancer. So we optimize that, and we will show you, not showing the data, but in the refractive surgery, they were applying 0.2%, 10 years, and there is no fibrosis happen, but 10 years later, this drug was so strong and proliferation was blocked and dead was, cells were dead for a long time, that the cornea started melting. So after 10 years, you have another set of problems. So we use 400 rabbits and identify the doses and duration of application, and that's what is used right now worldwide. So that makes me, recognized in the field first time in 2006. And then we have used the gene therapy approach for these different genes, and then to block the keratinocyte differentiation. The idea was, let's not have too many myofibroblasts in the beginning. We should control that, which if not removed, cause the fibrosis. So let's have them less, let the wound healing process go 1 or 2 days extra, but there is no fibrosis or vision loss. So that was the approach, and it did work. And I'm happy to report that this is, Decorin is the gene therapy which we optimized 2011. We have done all these animal, in vitro, and other safety studies in the lab. Now one of my student postdoc, he has moved here to India in Narayan Metralaya, and we are going to run a human clinical trial with him. So in the Bangalore, very recently. And then, of course, the MMP inhibitors, we tried all these inhibitors and all that. They all worked, but not impressively. There's a lot of variation, so we cannot move to the, academically they are good, but towards translational application, I don't think they will work. That was my view, so I didn't pursue too much. And then epigenetic regulation, most likely the reason I didn't pursue too much because I found a new area of working epigenetic modifier which are very effective, very safe in preventing corneal fibrosis. In fact, they have potential to serve as an alternative for mitomycin C, and that's what we are working on. We published it, and that's also going to be clinical trials soon. So with this, we have developed all these different drugs here. You can see this is all these different ophthalmic solutions we have developed using a small drug, and Dr. Panda is not here. We have used the Immodo, is also a plant product, which has shown a lot of interest. There was a Chinese girl, she wanted to do it, and I said no, but she insisted, and I said, well, let's go ahead. So we did it, and it did work very well. She got many awards. So all the students sitting here, I think we have a lot of medications or plant products in India which have not been tested. None of them has been tested for the eye, especially for the cornea in treating. And you have to remember, which we don't say that often, now everyone living after 40 years, that's my hypothesis, requires some kind of medication to stay fit. And our grandparents and parents and all that, they all live 80, 90 years, never went to gym, and ate all these food which is discouraged these days. And the reason was they were just working, and they knew, so all the Indian cultural tradition and foods are customized in a way if you think very scientifically, it never let you develop any disease. If you follow that pattern, and moderation is the key for all these different, dietary supplements. So, but I'm not talking about these. So here is the gene-based therapies for treating corneal diseases, which is my niche area in there. And here is the Dacorin, here is the BMP7, which is the TGF-beta family contract, TGF-beta family member, and it actually sequesters the TGF-beta. HGF is the hepatocyte growth factor, which is another, it does many of these things, and I will talk about it. And then there is the TGF-beta pathway, which is SMAD, and then there is a transcriptional pathway which goes down the stream. So from the very upstream to the down the stream at the wall, we have tested every single, step, and we're trying to see which one can be more translationally applicable to human and at the least dose and highest safety. That is our major goal. And then we have developed this SMAD7 and STGF-beta. This is all published, and here are some publications which are published here. So what I'm going to show you the potential of BMP7 and HGF combination gene therapy. This is for pre-existing corneal scarring. And the reason I'm doing that because I am also senior research career scientist in the Department of Defense in addition to this job of the University of Missouri. And they have many of these veterans. They got injured and they have the cornea which have the scar and all these things they cannot see. So I've been asked specifically to develop something which can reverse the process. So this is the one which can reverse the process. That's the first thing which we were first group in the world to show that. And of course this is the target pathology in the human which we want to treat. And of course to study that we need to have a human model. So we developed this representative rabbit model which shows that. And of course, believing the gene therapy is not easy. It's failed only in the eye it has worked. So the reason it worked is I studied more why the gene therapy failed in the other system and why it can work in the cornea and in the eye. And that's what I reviewed and looked. So these are the different vectors, which is no big deal because everyone used the virus vectors to deliver the therapeutic load. So which we tested it, identified for the cornea, all these various associated virus vectors, lentivirus. We screened all of them, we identified them, and the nanoparticles. Nanoparticles are very powerful because there's many different properties which come through nanoparticle and virus vector cannot provide that. And I'll be talking about more later. And then, the one thing which I have done voluntarily, my mentor was a clinician and he always said, why don't you come in a clinic? I said, what I will do in clinic? He said, no, just watch. So I used to go there and I really enjoyed watching this. And what has happened, so all these procedures, what I am showing you here, they are used in clinic. What I did when my things fail, I think all the time go back and apply that and change it in a way that make my failure too successful. And that's what we have done, and we have identified different vectors, and then this was, essentially the gist of this thing, that efficacious, optimized, efficacious and safe, targeted gene therapy method using the combination. So just alone using the strongest vector does not work. It's also very important how you deliver. Just having the best car will not give you the pleasure unless you have a good driver and best car in this. So nanoparticles is a multi-cargo vector, and we have screened many of those with our collaborators from India, from other countries, from UK, Japan, and all that. But we're focusing mainly on two hybrid GNP, gold nanoparticles, and PEI. And the reason nanoparticles is very attractive to all of us is because of their size, inertness, biocompatibility, and multiple molecule encapsulation. What that means, you can add multiple features to this delivery system. And then easy DNA binding and release, no tedious chemistry, but you need to know chemistry. And that's where my chemistry knowledge helps. and which is why I was asked to serve in every cornea in eye nanomedicine committee because of my chemistry knowledge. So you see, like 10 years I 12 years I studied too much chemistry, then next 10 years didn't study any chemistry, and then suddenly after this problem you just handle that. So that helped, and it is working great. And then human disease treatment with no side effects, simple fabrication and easy commercial production, less DSL2 requirement, and I call it GPS-like delivery system potential. So the nanoparticles which I will be talking to you is the size is 2 to 12 nanometer. It's a water soluble, stable at room temperature. It's biocompatible, excellent cellular uptake, slow clearance, bind DNA, and low toxicity. And this was developed by here and in this world. I must tell you, this Dr. Sharma, Ajay Sharma, he is a PhD of Punjab University, Pure University. He did PhD here with Dr. Manjeet Singh, for which I signed the program. His name was listed. So I called him, and he said, "Oh, this is very good. You should go there." He is right now associate professor in the Chapman University. So he was a part of this study. He contributed a large in this work. So with this approach, we were the first group to show in 2005 gene therapy is possible in cornea. And then these are other studies which shows the potentials and all that. And then this is what is the three-dimensional thing. What you see here, we published, this is the corneal epithelium, this is the stoma, and this green thing is the therapeutic gene. And how we did it. So the major thing is, everyone was surprised, how can you get this much of the gene transfer in the stoma? And I will tell you in the next slide how we got it. So this is how we did it. So we used this, they used to apply this drug in the clinic. So we came back and did it. So the main reason for failure of gene therapy in the eye is the epithelium, which was doing its job. Its job is to provide a strong barrier, not let anything to enter inside the eye. And it was doing its job. So we removed that. We put this one to have the vector and apply. And it did work. So that was the first study that was very exciting for us when we see the gene transfer, which I showed you in the past later. But we realized that it cannot be therapeutic. So again, one day I was watching in the clinic and I see one of the clinician and nurse was applying the hair dryer on the patient. I said, "Why are you doing this?" She said, these are the Fuchs dystrophy patient. Fuchs dystrophy is the corneal endothelial defect. So endothelial function is to pump the extra fluid from the cornea out from the cornea towards acrostium in the back of the eye. So, and what happens when there is not enough cells are defective, more defective cells, the pumping function of the water is compromised. So all your water stays in the stroma, and what it makes it swell. Once it gets swell, all the collagen structure gets deformed and everything becomes blurred. So they cannot see. So what she was doing, she was applying the hair dryer, gradually evaporating all the water, and after 10-15 minutes the vision comes back, its cornea becomes clean. So I said, "Oh, this is cool." So I went back and thought about it. I said, in the normal eye, let's take all the water. So I applied the hair dryer and then took all made dehydrated tissue essentially, and then applied vector, and boom. Then that's what happened. And you see like how much vector, at least 30 to 40 times more therapeutic gene we could deliver. And since cornea is we just dehydrated, so it cannot be overhydrated by applying the vector. So that's a very simple. So this is partnership between clinician and basic science researcher is very important, and it's always very tricky. They don't understand what we do, and we don't understand what they're talking. So we have to come in a way, in a manner that each of us can get in agreement. And they do. Once you develop it, the working relationship, they understand. So I believe you all should be talking that Dr. A is better than Dr. B. And he did the surgery, it's terrible result, same surgery, same thing, same tools, same machine, but the outcome is different. Why? Some can be the patient's variation, but there can be another factor. And that was the one reason which proved this. And the second reason, after we did this, everyone was so excited in the field. And in the next RO meeting, which is the largest eye research meeting, I was challenged. I said, what we do doesn't work, only in your lab. I said, why? And they said, we tried so many times, it never worked. So I said, I can't answer your question right now. Give me some time, maybe next year. So I went back to the lab and we asked the same question to all our students. And I was on the actually bench doing all this. So, and when again in the clinic, when I was watching this, doing this laser surgery, so all the time they remove the epithelium from the eye before applying this laser. So my mentor is a clinician, he was a clinician. He always tell them, all the residents, remove the epithelium. And their resident and all these medical students and junior doctors always have like heated argument with me. He said, you're the only one who emphasize. And what is the reason? Because no one else says you do it. You should just remove that. And he said, no, I tell you this is the patient outcome is better. So, and he did not have any scientific justification. And he is a clinician scientist, so he just, whatever he does, he just pays close attention as a habit. So then I said, when people challenge me, I said, this could be the reason, because he always taught me you should and must do with 45-degree angle. When you scrape the epithelium in the eye, just handle the blade with the 45-degree angle. So it's just part of habit. We just have a lot of us have a habit which we don't realize it. That's unique for us. We just do it. And so I always do it. So I said to my student, I said, let me scrape here and you scrape, we just scrape like randomly. We call a resident and say, you scrape it. So he scraped it, I scraped here after marking and here, and this is 4 area, 1, 2, 3, and here is the corneal epithelium. And then after 4 hours, we sacrificed the rabbit and did the tunnelization. So we tunnelized tells you the dead cells. So what you see in the area where I scraped, very few, 1 or 2 dead cells. Whereas in the epithelium stroma here, there are a lot of dead cells. And this is again came from my previous work of the hypothesis that what we have proved that when we remove this epithelium, there is an immediate keratocite apoptosis which happens. And we hypothesized and wrote in our paper, this is a redundant mechanism for the eye to prevent infection going inside the eye. So what happens, the cells immediately after injury go in apoptosis, die and make a sheet of dead cells. What works as like a barrier for any toxicant to enter inside the eye. And that's what was happening. So I presented next year, and that work was considered the most innovative research in the Harvard at that point. And it has changed the field entirely. So with that, we had a working hypothesis, localized and controlled therapeutic UV into stroma via developed topical methods, treats corneal scarring in vivo effectively without significant side effect. So one thing you might have realized in my research, there is more common sense than very rocket science. When science is science, but common sense is very important when you do. Anything you do, common sense is very important. So Apple do the things with common sense and paying attention to what we're doing. That's the important. So here's the BMP7. It's expressed in the cornea, modulates PGA beta, regulates excessive moving, and it's FDA approved in 2000. Was first time reported in the science paper, and so I was a very young, I think assistant professor there. So my major focus was in the lab to identify anything which is new. It doesn't matter. I don't understand even in all many of these papers which I published before. I wrote in discussion. I don't know the relevance of it. We'll figure out later. But this exists, and we need to know why they exist and what they do. We don't know how they functionally, modulate the vision process. So that's what happened, and it took me like 15 years to recognize it, what happens. And then, and so here, which I'm showing you here, they have started selling all these, fractures, what they put in the bone, and steel rods. They comes with the BMP7 coated protein. If you just, have you, I know most of you know, when there is any broken bone, it used to be 6 weeks to 2 months or 3 months of the cast. Now it's usually 2 weeks, everything is healed. Why? It's because everything what comes now is BMP7 coated. So it promotes wound healing so much that there is no need for that extended period of healing. So with that, we have delivered this BMP7 protein in the rabbit cornea using our method. So you see here, this is the normal. If you don't have BMP7, here you do BMP7, there is a significant reduction in the myofibroblast cells. And then we identified the mechanism, how it works, and it was published later, and that's pretty much it. And the other molecule, which is hepatocyte factor, I told you, and you read the literature, it does every single thing. It controls fibrosis, angiogenesis, immunotolerance, inflammation, apoptosis, and regeneration. So when a student came, he said, sir, it does everything. I said, then what's wrong with it? How can we do it? I said, it does everything, but have you paid attention? It does everything in a very different way. And it does one thing only in one system is not. So it should be microenvironment. Let's talk about the microenvironment, how it plays a role. And then we identified and we showed that. And it regulates many functions. And as I said before, during my postdoc and early days of US when I go there, my emphasis was just to identify and do the very, what we say, sensational science. Just do something which no one has done, just report it. And that's what we did. So we did this, there is a HGF, so we did this cornea, and then we got the mice, we did this, and then we here in this group, BMP7 and HGF. And you can see after 2 weeks, you see here and how the cornea becomes clear. All this cornea is getting clear. And in 4 weeks, it's a very significant, robust response. All that from here to, if it stays here, from here it gone like completely transparent. Then this is the slit lamp, which is a clinical examination. If any of you have seen ophthalmologist, they ask you to put your chin down and look in the light, and that's what it is. So they do the eye exam with that, so we do it in the lab all the time. And then we did the standard pathological testing with the HME and then immunohistochemistry to make sure that these myofibroblasts are gone, which is what we see. And then we did this tunnel assay here and double staining. So you see this tunnel assay here, which is going in, and here you see this SMA is dramatically reduced. So we were very excited, and we submitted the paper and it does show that if you deliver these two genes, BMP7 and HGF, so we just showed this if you submit it, the reviewer said, all you're saying is right, but how do you believe this is selective? This is your presumption. And they are right. And of course, that was our presumption. So how to prove that? So to do that, we used the established in vitro model, which we showed you in the past. And what we did, this is transparent cornea. So you see all these red. So these are the double staining, green is the SMA. So what you see is this selective apoptosis with the HGF happening only in the myofibroblast, but not in the corneal fibroblast. And that is the transparent cell, and this is the opaque cell in theory. And that was then this paper was published. So then we were excited, we wanted to go for the human clinical trial, and then to do that we had to do long-term safety studies. And of course, initially we planned for 6 months, but because of COVID, we didn't have any access. So we had to go to the lab, so we just turned out to be 7. Which for this study did not matter, because it was long-term safety study, it was good, but essentially, everyone asked why you picked 6, 7 months, that's a very odd number. And that was essentially the reason. So basically, when we did the safety study, we just delivered the gene and vector and the knife. So knife, naked vector, and the gene with the vector. And we deliberately did not do the injury, just to make sure that we study only how safe this KT and vector is. So we did that in slit lamp examination. This is a complicated picture, but what I can tell you easily, you see the one line. If there is a 2 lines, that means the cornea has a opacity. If there is a 1 line, that means cornea is clear. So in all these where the gene is vector was delivered and gene was delivered, everything is a single. That means cornea is transparent and clear. So then we did this 3D in in vivo confocal imaging, and the power of this HRT, RCM confocal microscopy. So in the eye, it just is make the digital structuring of your each layer of the cornea, epithelium, and middle epithelium and all that from anterior to posterior, and that's what we did. So this is superficial epithelium. And all looks similar in all the 3. This is middle epithelium, all looks good. This is anterior stroma, everything looks good. There is some increased number of the keratocytes, but they were not statistically significant. And this is mid stroma, no change, everything looks same, easy. The number of cells are same thing with the posterior stroma and endothelium, same thing, no negative responses. In the endothelium. And then we did the pachymetry. Pachymetry is the technique where we measure the thickness of the cornea, which is also very important. And in the first, 1 day, there is some difference in the vector and vector delivery, which was expected because remember our technique involved removal of the epithelium. And then shimmer test with the tear volume are also very important. We should not have abnormal tearing and low tearing. Abnormal tearing is back and low tearing called travel. So we tested this tear value, and of course it's all same up to the 7 month in all the three groups, naive, vector-alone, and therapeutic gene. And tonometry is the technique where we measure the intraocular pressure, which is an indicator of glaucoma patients, whether the patient is going to develop a glaucoma or not. And in all the three groups, there is no change in the intraocular pressure. So essentially, this thing will not cause any glaucoma disease. So, of course, histology is another thing. We need to make sure that the cornea structure remains same. So this is live, this one, and this is all at 7 months post anesthesia. And the Mason trichome measures the collagen volume, or you can say quantification amount. Collagen is very important for the cornea. It's there, and blue color is the one which is representing the collagen level. So you see in all the three different groups, the collagen level was found. So based on this, gene therapy offers a powerful method to treat corneal scars and restore vision. Dual gene therapy effectively treats pre-existing corneal scars in the rabbit cornea in vivo. No clinically relevant side effects observed in the rabbit cornea until 7 months. Safety and mechanistic additional studies are underway. And I am just presenting all the good work of all the students who really work very hard to do all this work. So all the credit goes to them. And of course, these are our collaborators. And here she is the ophthalmology chair in the All India Institute of Medical Sciences, Bhopal, where I will be bringing all these medical students in the May and June for 2 weeks, and their medical students are on there. Here is Dr. Rohit Shetty, who is the CEO and ophthalmologist in the Narayana project, and we collaborate with them. And here is the Alka Subra Ghosh, who is the director for their gene therapy program, and he did a postdoc with me from 2008 to 2010, and then he relocated back in India. So with this, I'll stop here. Thank you for your attention, and I'll take the question.
Professor Mohan, I think this was a very interesting talk on corneal blindness and how gene therapy is helpful. Before I ask the audience to ask questions, out of my own curiosity, I will ask 1 or 2 questions. Any initial symptoms which can warrant our attention that the cornea is losing its transparency and becoming opaque? Any initial symptoms?
It's just blindness. Patient will tell you they can't see. It's just you cannot read. All the letters will look blurred. So that is the symptom. And it happens, after injury. Anything injury, you often see the blurriness, and of course tearing and all that. But it usually comes back if healing happens properly, which I would say 80% of the time happens normally. So that's why 80% people regain their normal vision after mild injury. So that's why we have divided. There is no one drug fit all can be existing there. There's only one thing which is steroid. No matter what level of, if the patient keeps complaining, the ophthalmologist, use the steroid, the prescribe.
Any association with diabetes or hypertension?
Hypertension, IOP, glaucoma, yeah, there is some. But that's why we say anybody who is a diabetes should get their eye tested every year. Must. It's very important. 2 things very important if you have diabetes, that you get eye tested and kidney function tested every year without failure. Because what diabetes does, it does a progressive, slow damage to both these organs. And both these organs are every organ is very vital. Of course, I am wired with the eye. I always tell, without eye and vision, have no life.
That's what I'm asking. Because in old age, maybe at times you feel that these kind of diseases may threaten you.
Yes.
So anyway, any questions from the audience, please?
Yes, ma'am.
Just switch on.
Be loud, right?
You can just stand.
You can come closer to the mic.
Hello. So you talked about BMP7 coated molecules and especially the protein which promotes long healing. And if we talk about keratoconus or glaucoma, the treatments in USA basically cost for keratoconus it costs $16,000 and glaucoma it costs around $2,000. But why are we not using growth factors, injections instead?
Yeah, no, very good question. So first of all, $2,000, $16,000 is a very cheap, from US standpoint, I can tell you. Okay? So, although from India's standpoint of standards very high, very much, but all these drug companies makes money only in US and invest in research. So, this is very cheap. This cost is after the insurance coverage. So, you don't know. But the reason we're not doing it because it has not been fully optimized yet. And this keratoconus, what they do this surgery which is the riboflavin. Riboflavin is vitamin B12, so they do the collagen cross-linking. As I said, what happens, what is the keratoconus? And there are a lot of patients in India, you won't believe it. So we've been working with the keratoconus and for which we are developing the LOX gene therapy. So what is LOX? LOX is an enzyme and a protein which binds to all these collagen and it makes them hard. So what is in the keratoconus? Your cornea becomes thin over time progressively, and once it goes below threshold, it becomes like the vision becomes blurred. So what the keratoconus and currently this cross-linking process, what is done is only preventative, it's not curative. Once they know this is happening, they will do the cross-linking to prevent, to make the collagen stronger so that there should not be more progressive. And you are right, this is a good question and very intrigued. People are working on it. And so don't be shy. Ask, no question is a stupid question. Okay? Don't be shy on that. Just ask whatever comes in your mind. Don't feel like what others will think about it.
Dr. Aziz,
yes, sir.
I was wondering the removal of epithelium that you mentioned, how effective it is in the sense that it depends upon the expertise of the person who would be doing it. Because sometimes everybody is not that expert to get to that technique. I was wondering what is the actually chances that it can be right, it can be wrong. What is the effectiveness?
The chances for rightness is 99.9%. So corneal epithelium is very different than the rest of the epithelium. It grows very rapidly in a normal patient. This is one of the most common clinical treatments. If anyone getting recurrent corneal erosion or recurrent corneal infection, so what they do, they just remove the entire epithelium, and the epithelium, what happens on the side of the eye, there is a limbus, and from limbus there is stem cell. So these epithelium regains within 72 hours, 100%, all the cells. So that's called XYZ mechanism. So all these stem cells come and they make the basal cell, and then these basal cells keep differentiating. So sometimes if your infection happening in this part of the eye, they don't scrape the whole thing. So they scrape the, that part and that will recover. But most of the time clinicians can do all the entire corneal epithelium. So for 3 days you will have discomfort because you don't have the cornea.
It is otherwise a safe procedure.
It's a very safe and very common procedure.
It was a very excellent talk. What I would like to know is your take on stem cell therapy because gene therapy and stem cell therapy they hiding have a lot of
Absolutely. Absolutely. No, you're very right. So when we did first time gene therapy, so we were trying to do gene therapy, not developing genes in the stem cell. When the shape of the eye this is dome shape, right? When we applied vector, everything spills off. Why did I started using the cloning cylinder? Everything spins off. and no gene was delivered in the eye, it was delivered in the stem cell. And you don't want to deliver in 1990s, late 1990s, you don't want to deliver any gene in the stem cell. They mean deliver anything, all the researchers will say, oh, stem cell, you damage the stem cell, so whole thing is gone. But now field has evolved. Everyone is talking about using stem cell for therapeutic use, which is what we are trying to do it. So, but my lab focus is not to develop the stem cell therapy. So we have sent a new postdoc to the Harvard, where we have a collaborating partner to learn about that, some of these ins and outs of the stem cell therapy. But right now, what we seeing it, how this mustard gas and all that impact the stem cell, because all these chemical weapons, some people get like immediate response or loss of vision. Many get like a delayed response. After 6 months or 1 year, they see the cornea become blood. And it's most likely because of some damage to the stem cell. Because the cells which are going to be replaced by them are not produced enough, are not to a high quality. We don't know that.
So can you comment on the success of gene therapy on the diseases pertaining to the uvea layer of the eye? In particular, uveitis, I wanted to draw your attention towards, wherein the antibodies attack the healthy tissue. So wherein the immune system comes into play.
Right. No, you're right. We not work in uveitis. We just work in the cornea, and many other groups are working, and they're having this challenge.
Because as of now, allopathy has no cure for uveitis. They just suppress the immune reaction.
There is no cure for any of the eye disease, you know that. There is none of the retina disease, there is no cure. All we can do is delay the process. Delay the inevitable. That's what is happening, all the retina and glaucoma as well as uveitis. And cornea as well. You know, all this genetic disorder is a keratoconus and also epigenetic factors are there too. All we're doing is just delaying it. So that's, and there is no, this is a sad part in the ophthalmology. All we have is just anti-VEGF drug that will help. And the other thing is the steroid and non-steroidal anti-inflammatory drug. They are not specific what they do, they just do your inflammation, reduce the inflammation, and once you reduce the inflammation, essentially you reduce everything. And it's global. It's not specific for any particular disease or particular tissue type.
I think in glaucoma, you are right, of course, it cannot be done. Maybe if people lost vision here. But in case of this corneal blindness, maybe the cornea can be transplanted.
Absolutely. But only 30% of the cornea transplant fail. Number one. Number two, you need the donor tissue. Okay, many people don't donate the tissue. Number three, all these younger generations are very affluent. No one wants like the classes. Everyone wants to go for refractive surgeries, right? Any cornea which has gone under refractive surgery cannot be used for transplantation. So it's right now not a major problem, especially for rich people, I would say. But it's going to be a difficult thing for everyone in the future.
Any other questions, please?
Yeah, all these students, if you're not asking questions, that means either I did very good job or I did very bad.
Of course, I think there will be better.
No, don't hesitate. Just ask them. You can ask later.
Yeah, they can ask later. So I think we express our sincere thanks to you for excellent talk.
Was a very interesting session. I request Professor Raman to please facilitate Professor Raj's comments.
ਇੱਥੇ ਕਰਾ ਲਓ
Okay.
I would request Professor Raju to please present the token of gratitude to our chairperson for the session. Professor Raju.
Yes, sir, please. Wait. Thank you.
Thank you so much for your keen involvement in the talk. Now I request our chairperson, Dr. Amit, to please give a vote of thanks.
So on behalf of the organizing committee, I extend a heartfelt vote of thanks to our chief guest for this session, Professor Dulal Panda, who was kind enough to accept our invitation and take out time from his busy schedule to be with us this morning. His presence has set the pace of this conference, and I am sure his thoughts have enlightened all the young minds who are present here. I am equally grateful to Professor Harsh Nayak for gracing the occasion with his presence. Thank you for sparing time and being with us. You have always motivated and inspired our efforts leading to the successful hosting of this conference. We are extremely grateful to Professor Rajiv Mohan, who has flown down from US after such a long trip from Australia and being kind enough to grace this occasion with his physical presence and enlightening all of us. I thank all speakers, invited guests, faculty members from different departments for gracing the occasion. A special thanks to all the participants and students for participating enthusiastically. I wish you all the best and hope you all have a pleasant stay in the city for the next 2 days. It is a privilege for all of us here at Punjab University to host you in our city beautiful. I sincerely hope you all will enjoy these 2 days of science, discussion, debate and networking. Once again, we welcome you all and thank you for being with us. I request all of you to join us for tea outside. Thank you.
All the poster presenters, kindly place your posters on the boards during this tea time.
अभी फूल गया
All the poster presenters, are named in the presenters who are in session 1. Please place your posters on the poster boards from number 1 to 35.
Singh and Professor M.D. Irfan Ali. I would now request Professor Prince to kindly introduce us to the first speaker of the session.
Thank you. Our first speaker today is Professor Shailja Singh from the Special Center for Molecular Medicine. She is also Director, Advanced Instrumentation Research Facility at JNU. She is a recipient of National Bioscience Award DBT and Gandhian Young Technology Innovation Award by the President of India. Shailja Singh ji is a trained molecular parasitologist with more than 19 years of research experience, and she has received many awards for her innovative work, like Innovative Young Biotechnologist Award in 2010, Senior Innovative Young Biotechnologist Award 2013, National Bioscientist Award 2018, and so on. Honorable President of India has given this award of Gandhian Young Technology Innovation to her in 2018. Her fundamental research on biology of human parasites has shown a great potential in translational research towards drug discovery and development. Recently, her work has shown a potential in improving the efficiency of an age-old anti-malarial drug, artesunate. In nanomedicine-based artesunate with the surface-coated ionoside nanoparticles has enhanced anti-malarial potential in P5 fever. I think she must be telling this all in her work. Dr. Shailja has more than 140 research papers to her credit with a very high H index, and she is a part of the International Center of Excellence for Malarial Research, USA, and funded by National Institute of Allergy and Infectious Diseases of the National Institute of Health. She has been serving as an expert of the Medicines for Malaria Venture in Switzerland, expert scientific advisory committee also. I invite Dr. Shailja for her talk today.
Already okay. Thank you very much. Such a nice introduction, and I'm really pleased to be here to present my recent work in recent trends in medicine. And I'm really very grateful for this invitation to my dear friend Avni. So she invited me, and I really wanted to come here to talk to my dear students because he is very close to my heart. I always prefer to come here to talk to my students. So today I thought of giving some hints what we do and how we engineer innovation. Again, why I call this term we engineer innovation, because every time when we talk about the modern medicine, modern drug discovery, we need to have some innovation component to it, because we have to show the progress that we are coming with a novel technology and we are also coming with a novel ideas to integrate in such a way that we can give the solution. And don't come again and say that you have a problem for every solution. So we need to have a solution for every problem, and we can do that. So at the same time, as I said, I am a molecular parasitologist and I focus on malaria and leishmania. And again with the focus that how I can establish or understand how the parasite interacts with the host, and by this fundamental studies that the interaction can be understood in a better way. If I understand the interaction, I am very sure that we can cut that interaction. Cutting the interaction can lead to the solution for disease, because that interaction is a key for establishment of any pathogenesis. If I talk about the infectious disease. So in that case, if we understand which is the protein, which is the molecule, which is the metabolic reprogramming leading to this interaction, and if at all I can come up with some solution to break that, I can have some solution to treat the disease. So in this case, like again, it's my very famous slide where I try to convince my all student and audience that yes, there is a still need to work on malaria, because we need to learn from the newspaper as well as from WHO reports that yes, the malaria cases are going down, but we have already given our promise that we are going to eliminate this disease. So So curing the disease is something, but to eliminate the disease we need to work more and more and more. And for that also we need a more innovative approach, because elimination is a real very complex term. If you want to eliminate a disease, you have to work towards all aspects. For example, you need to understand the disease, you also understand the therapeutic regimen, you also need to understand in case of malaria the vector which is responsible for transmission of the disease. Then we have to also see what's the setup if we want to go and talk to the people who are more affected by this disease, how we can convince them for complying with the whatever policies and strategies we are making to eliminate any disease. In terms of my focus area is the malaria. So again, just to give you the glimpse that malaria is transmitted through the mosquito, Anopheles vector, and then it is a female Anopheles mosquito, and the female Anopheles mosquito takes the blood meal because of its protein requirement for egg laying capacity. So while she takes the blood meal, it also leads to the transmission of the malaria parasite from one human to another. Now, if I say, if we want to really tackle this disease, what we should be doing? Either kill the mosquito, either kill the parasite in the human, or kill the parasite in the mosquito, don't kill the mosquito. So with all these things there in the plate, where we would like to go about. So researchers have their own domain. Some people are working for novel insecticide development. The modern researchers are also working to make the genetically modified mosquitoes which are free from the parasites. So if you release to the environment, they are not going to transmit the malaria. And a basic researcher like me, we are trying to understand the parasite in the human, how the parasite is interacting to the human cell, and that interaction can be blocked to cure the malaria. Basically, everything is linked to the elimination program. And at the same time, as I said, that it still is a burden in case of the tropical country, which includes malaria. My group in Jawaharlal Nehru University, we are really very big group, like around 25 members are working towards leishmaniasis and malaria, and we focus on 4 core parts. We do the molecular signaling and cell biology, interdisciplinary sciences, molecular epidemiology and ex vivo work, and synthetic biology and molecular medicine. So in case of molecular signaling and cell biology, we try to, as I already discussed, we try to understand the host-parasite interaction part. Whether the signaling is involved in the interaction, whether any molecules are involved in the interaction, and if at all we can know more, we can come up with some of the good targets to develop some small molecule against those targets. We also do the interdisciplinary science, as I said, that because we are working on a very deadly disease in case of parasite, yes, it is. So in this case, we are trying to see that if at all we can develop some good carrier, and like nanoerythrosomes, now we are developing to deliver the vaccine candidates. We are also coming up with some of the new platform. We are also developing some new assays to screen the small molecule inhibitors for anti-malaria. We are also doing some synthetic biology and molecular medicine work, where we do the phenotypic drug discovery, taking the peptides, microbial peptides. We also screen them for immunoassays. We also take some phytomedicine approach. We do some molecular medicine, like for example, we have isolated some miRNA from red blood cell. You will be really surprised. Recently we have published a paper. Our red blood cell also contains some microRNA, because they are also coming from the progenitor cells. They harbor some, and they also put a difference against parasite, because the parasite is going to be red blood cell, and that has the microRNA. So we also understood the interaction between this microRNA, if at all it is there in the host, how it migrates to the parasite, and in that case, can we design some molecular medicine against the parasite? And that was the work here. In the molecular epidemiology work, as I said, the malaria elimination program is just not you are working on the parasite. You have to understand, if at all, what is happening in the field. Is the parasite coming up with a new resistance? If we know, then only we can prepare it to tackle that resistance. If at all there is a multi-drug resistance coming together, is there anything happening to the host in terms of the human? If they are becoming resistant to the parasite, or they have some genetic trait which is defensive for the parasite. For example, the sickle cell anemic patients, they are again refractory to the malaria parasite.
They have developed this in a long evolutionary mechanism. So in that case, the question needs to be asked, okay, host has changed itself. Can we also think of something where host should be benefited? Let's say if I want to treat the malaria parasite in a cyclic patient, they are already cyclic, they have less parasite load, but they are resistant to the artemisinin. So I need to have some novel solution. So for that, this area of research is very much necessary. So that's what it's a really vast area and all together venturing into. And sometimes I get criticism also, like why I'm touching all the area, I should be focusing on one, but it's my own desire to do the research and this is the way. So to the student, just a very brief introduction, how malaria parasite goes inside, how it interacts to the host, how it establishes the pathogenesis, and you can see this. When an infected Anopheles mosquito, it bites the human, it injects the malaria parasite in the form of sporozoite, it goes to the liver, it proliferates in the liver, and when it comes out from the liver cell to attack to the red blood cell, when the red blood cell it is being attacked by the parasite, again the parasite continues the life cycle in the red blood cell, then some of the parasite they really, after this stage or during this stage, they just start transformation. And that transformation is for the male and the female lymphocyte. Again, when the mosquito picks up, it picks up the male and female lymphocyte, and then they fuse, they form the zygote, rutinate, and finally they also establish the interaction in the mosquito with that, and finally they form the sporozoite and go to salivary gland, and again, when this infected mosquito bites to a new human, the next human, then infection. So many fundamental questions arises, and it's like a full of questions, and really a pleasure to read between the lines where one can venture. And again, the liver stage infection, it's how the liver cells are interacting to the parasite. This is again an area I am working on this area, but in the red blood cell, it's very simple question: what are the proteins of red virozoite interacting involved in interaction with red blood cell, and if at all they can be a vaccine antigen, because if that protein is helping the parasite to interact with red blood cell, you just come up with the antibody, and that antibody will block the interaction with the virozoite with the red blood cell, and you have a vaccine antigen. The same thing, this is already been I have also identified around 10 to 15 antigens, and to my surprise, only one antigens are now we are taking it further. It can serve as a good vaccine antigen. It has recently been published as a C2 domain containing protein from the liver. But at the same time, once you are done with the interaction, you will go towards this stage where the parasite is now inside. And inside the red blood cell, what it is interacting to is also important, because it has to be there comfortably, and for that has to take some of the food material from the red blood cell, like a hemoglobin. So in case we need to know what? We need to know to develop any drug here, we need to know about the transport, what is the parasite transport mechanism to take the nutrition from the host to the parasite. Then we can also see if at all hemoglobin is being taken up by the parasite, how parasite uses that hemoglobin. It has to be, there's some enzyme, proteases to chop, to convert it to amino acid, and that only will serve as a building block for the parasite growth and development. And then once it is properly grown, mature, multiplied, what it will do? It will exit, because it has used all the resources of the host red blood cell. It has to continue the cycle. It will go to the next host. So in that case, what it will do? It will just exit from the host by disrupting the host. And you know, when malaria fever comes, we get chills. Why we get chills? Because that time the parasite in a synchronous mode, they all are busting the red blood cell, they are coming out. And that's what the fever with chills is the very, very critical symptoms and diagnostic symptoms for malaria infection and the fever. So in that case, what is the mechanism for basic researcher to look for? Why the parasite knows now I am mature, I have to come out. What is the machinery helping parasite to come out? And what is the machinery again, as I discussed, which helps parasite to get in? That is an invasion machinery. But now I'm talking about the exit machine. So if you want to have some solution, what one can do, one can ask for exit machinery, block it, block it. You are blocking the exit machinery, you are locking the parasite inside the retina. Or again, block it to invasion. So there you are not allowing parasite to next invasion. So I also thought of doing more towards this area, exit and invasion. So I wanted to really lock up the parasite. And then when I am doing that, by making some more understanding about the machinery, I also thought I should block these dermatocytes also, because they also need to come out. Because the exit of the dermatocytes from the red blood cell is very much necessary for fusion. If I can block it, block them inside the red blood cell, they are not going to come out, they are not going to fuse. Transmission is going to be handled well. So there, and this mechanism and machinery, to that my mind it must be similar, and that's what we found it. So the next thing, which as I said, the exit machinery, where I really put lot of efforts, almost 7-8 years, where we could show some of the proteases which helps the parasite to degrade or dismantle the red blood cell. We also come up with some of the calcium dependent proteases, normal proteases, protease maturation machineries. So these are all my papers one can see. However, we also come up very new concept of perforin-like proteins. So these perforin-like proteins are being coded by the human malaria parasite. They form the pores. Because as the name suggests, we also have in human perforins, which you must be knowing. So the similar, why I am calling it perforin-like, because they are not perforin, they are there in the parasite, but they look like perforin. Because they have also the central domain, which is very much responsible for pore formation. And the pore formation in the host, and that helps in what? Dismantling of the host, and that is very much necessary for what? Exit of the parasite. So again, to exit, the parasite expresses some of the perforin-like proteins to and exposed to the red blood cell membrane, and that makes some pores, so the osmotic influence or the osmotic disbalances happen, and the parasite happily comes out. Anyone can ask me the question why it is happening only at the very maturation stage. Again, I say the regulation process is such a good in the human cells or in the parasite cell that these proteins are only expressed at the very late stage. Their discharge is so critical. When they want to come out, that time it will discharge to the human red blood cell, and that's what the pores will form, and then parasite gets help for its exit process. What was the aim then? That is, this perforin-like proteins, are they only there in the red blood cell stage, or they are there in the liver stage, or in the dermatocyte stage, or also there in the mosquito stage? Because everywhere there is an entry-exit games are going on. So in that case, if the machinery is same, proteins will be same. They might be in the same family protein. So yes, it was very logical, very rational, and we found protein 1 family member was there in the liver stage. PLP1 and 2 were expressed in the blood stage. PLP3, 2 and 4 were expressed in the dermatocyte stage. PLP3 and 5 were there in the cyst stage. So that all make my life very easy. That okay, there is a family of protein that is being expressed by malaria parasite. They are well distributed among all the life stages. If I can have a solution for one domain of perforin-like protein, I may have a solution for all stages. And blocking all stages will help me what? Curing malaria as well as the transmission blocking of it. So it was a very good question, but we had some challenges. As I said, the first thing is always, even as a researcher, we face problem that regulation. Everything should be regulated, it cannot be regulated. So in that case, regulation machinery need to be learned. How this protein being discharged, what is the regulation, how the parasite knows now that I'm ready with the protein, but I will never be able to discharge unless and until I will get a signal. So then, like in my past postdoctoral research, I worked on the calcium signaling, where I could only suggest that the calcium is involved in the exit machine, but I could not link it with the how this calcium surge is involved in the perforin discharge. So thought of just showing this. So again, this is a very interesting movie where I Professor Bilal Panda described that how he looked for the microtubule dynamics and that microtubule dynamics in a live cell by using the biophysical techniques, how it is possible, is very interesting. Similarly, I wanted to see that when we say that we have the parasite in our body, it's going from one cell to another, it's coming out from one cell, how it looks like. Whether the process is regulated, what's the time frame, what is being, whether the calcium is the regulatory factor or not. So in this case, again, it took me really almost 3 months sitting under the microscope all the time looking for this eureka moment, because it's very, very difficult to mimic what is happening in the body. And the similar situation you are giving under the microscope, human red blood cell parasite infected maturity, lasers should be low, not to be toxic, calcium to be loaded indicator, and then wait patiently with your coffee that yes, can you see that? So in that case, yes, I could find, and not only this, like almost 30-40 events I could see, and you will now enjoy this. So here, this is a charger. This is a glass. Here is our schemo. One needle was attached to the new red blood cell. Invaded. You can see during invasion what happened, because the new red blood cell, it was tremendous under pressure. It has to accommodate a new parasite. So there is a process known as echemocytosis. Calcium went up. Again opened a question for me whether this surge in the calcium is important or not. Then again we will come up with any publication on that. But here the aim for this particular talk to tell you that exit mechanism is very well regulated and regulated through calcium. And then in that case, this time the exit is, we have already shown that we have this purple like protein coming to the surface in my major communication paper, however I am going to show it. But this purple like protein is a real bad protein, because as I said, it helps the parasite, but at the same time it also contributes to the pathogens. When the malaria parasite is there in our blood, it is discharging this purpurine-like protein, and then this purpurine-like protein, what it interacts to? It also interacts to the host cell, the endothelial cells of our capillary, and in that case, it also leads to dysfunction of our endothelial cell. I wanted to understand that how this dysfunction occurs, because those dysfunction in the endothelial cell leads to pathogenesis. We all know that malaria pathogenesis is how it is been exerting all these problems. This is due to the vascular dysfunction, occlusion, it also anemia, because it causes severe anemia in the children who are suffering with the malaria parasite, because it leads to the damage to human red blood cell. It also leads to the hemolysis of red blood cell, and that leads to anemia. So in that case, as we express the purpurine-like protein, I just added this purpurine-like protein to human endothelial cell to see what it does. So you again can see how these proteins are really funny and how they can interact with the host cell, and you can see there is a bleeding started. And this bleeding process is totally induced by the human malaria parasite purpurine-like protein, and then cells responded to that in a nanogram or in a picogram protein from human malaria parasite could lead to the real damage to the human endothelial cell. But it is just the bleeding process. We again process it for the apoptosis. Ask the question for all apoptosis phenotype. Our keynote speaker, he really discussed about the apoptosis, like tunnel assay positive. Then there are also the HMGB secretion to the cytosol, confirming it is necrosis or the apoptosis or necroptosis, all this being done in a very detailed way. And then I also wanted to link it with the annexin positivity, PI positivity and calcium surge, because that is also an indicator of apoptosis or necroptosis. So you can see here the cells are going green. Green is the calcium, then they are going red, that is propylium iodide, just because I am adding the toxin to it. Toxin meaning purpurine-like protein from human malaria parasite. So that confirms that human malaria parasite discharges a purpurine-like protein to the blood stream that interacts to the host endothelial cell, and that interaction lead to dysfunction. But at the same time, as I said, I also wanted to see whether they also interact to any bystander human red blood cell, and for that, again, the same story repeats. Whenever we put the purpurine-like protein, we see the red blood cell are going green, calcium surge is there because they can form a hole, small holes, and then this retiноcytosis process started. They become very spirocytes, and then they swell, and then finally they discharge. And that hemolysis process can very well link with the anemia caused by the human red blood cell. This is the annexion positivity, then we add the recombinant purpurine-like protein. And again, to show it in live, you can see here. So we just added the purpurine-like protein, and these red blood cells were loaded with the calcium sensitive IO4 and then you can see all of these cytosis started, they became green because but this is just a very observative thing, right? You would ask me to really know, madam, pore is there or not, show me what is the size of the pore, whether the pore is coming from the monomer form or oligomer form, all those biophysical techniques we use, then we could convince that yes, by atomic force microscopy we could measure the pore size, and we could also show that there is 8 monomers of purpurine-like protein, they come together, they form the oligomer, and those oligomers go inside to the membrane and then form the purpure. So those details are there in the paper. But the aim was to know the fundamental part behind this thing. But at the same time, we also wanted to have some solution, as I told in the beginning. And for that, we developed some small molecule. So as I said, that the monomers form an oligomer, and these oligomer only goes inside to the membrane. So you can have many types of approach to block this purpurine-like protein. Don't allow them to form monomers. That means you design the molecule which will be in the interface of the two monomers. So in that case, what will you do? They will not form an oligomer. If they will not form the oligomer, they will not interact with the membrane in a barrel-shaped form, and there will be no pore. So in that case, again, biophysical techniques helped us, where we took the monomer, we saw very nicely they are forming the oligomer, but in the presence of compound, they could not form the oligomer. Okay? But at the same time, you can have a sealant. Let the oligomer form, but in the pore, you can have the peg-like molecule, where you know the pore size and you know the molecule, and that will just go and sits on the pore, and there will be no exchange of unnecessary things, fluids, so you can have the sealant molecule. But that was not our approach. Our approach was to block the oligomer formation, and we interacted with the chemist collaborators, and they could very well design, and they could show that these molecules, they bind to the interface, they block the oligomer formation. And again, as I said, we needed to prove that, like other than other biophysical techniques, that yes, in case of this is a smooth red blood cell membrane, and then as soon as we put the purpurine-like protein, we see there are pores, and when we put the C01 compound, then that does not allow the oligomers to be formed, and there will be no oligomers, there will be no insertion on the membrane, and you can see again that the C01 was also like this replicator to the protein. Now the question is being solved. You have a molecule which blocks the oligomer formation, it also blocks the pore formation. Ask the question whether it blocks the exit of malaria parasite or not. If it blocks the invasion of or not. And yes, both were really very phenomenal in terms of their blocking efficiency. And then again, as I said, the invasion and exit both were blocked. And in my first slide I showed the gametocyte egress is also important for transmission. You can see the gametocyte exit can be analyzed by X flagellation assay. So as soon as you activate the gametocyte, you see them dancing and you see their fusion. But in the presence of these compounds, we could not count that event. So that itself shows that they are not exiting from the red blood cells, so they cannot make some X flagellation centers, and finally they cannot fuse and form the transport protein. but at the same time the sporozoite was also being used. And then it is the malaria part. I also wanted to show the protection part. As I said, this perforin-like protein attached to the human red blood cell. It causes the hemolysis. So in the presence of drug, the hemolysis annexin positivity was totally aborted. So they were protected, and this part was published at home. And then, how much time I have?
Okay, you have still time.
Yeah.
Okay.
Okay.
10 or 10, 15 minutes.
Okay. So as I said, the gametocyte exit is quite important, and their exit is very well regulated through calcium, and and this regulation through calcium discharging of perforin is linked with the formation of this X-linked dilation center. But with that information, again I asked another question, whether there is any sensor protein which can sense the calcium. Apart from, so executor protein is perforin-like protein, signal is calcium. What is in between? In between, I could show the perforin-like protein, petatin-like protein, which is like they are very like plant, but they are in the malaria parasite. That is being regulated through calcium and responsible for perforin-like discharge. So this is our PNS paper. One can see that very beautifully we have shown the CRISPR-Cas approach we took. We deleted the petatin-like phospholipase from the human malaria parasite. Then we put the calcium signal, and we could not see any exit. So now we are proposing, apart from perforin-like protein, there is a phospholipase which regulates its secretion. So you can also come up with some of the inhibitor for this against this petatin-like phospholipase. And we have those inhibitors. We are coming up with a new paper where we are showing that from the 10,000 compound libraries, we have screened some small molecule against this petatin-like phospholipase. They are blocking these the secretion of perforin-like protein, and finally blocking the gametocytogenesis. For any approach, again I said the target identification and drug discovery is a complex process. Everything should go together, and to have more and more target, you need to have some proteomics, transcriptomics approach to at least have some of the repertoire. And for that, from that repertoire protein or target, you can search which one is the important one. And for that approach also, we also analyze the phosphoproteomics of human malaria parasite megazoids. And from that phosphoproteomic analysis, we could identify a cluster. The cluster is what? Calcium-dependent protein kinase 1 interacting to protein 3,3 molecule, and that interaction is leading to protein kinase A, and the trios are making again a very good friendship for the parasite growth and survival. So again we have a target, CDPK1 can be a target, protein 3,3 can be a target, or PKA can be a target, or their interaction can be a target. So going through this, yes, we have done a lot. CDPK1 as a target, we published. Again 10,000 molecules we screened for CDPK1. We could show they are targeting the CDPK1, they are blocking the human malaria parasite growth. Then, as I said, protein 3,3 interacting to CDPK1, either target protein 3,3 or target the interaction. We targeted the interaction of protein 3,3 versus CDPK1, and targeting the interaction of the two protein again was a very good idea. Again, this is perfect. Then the next thing was that this interaction is also calcium dependent, so novel protein in the cluster, and then as I already discussed, the superhuman protein we have also been able to show that we are good energy. This part I have already discussed. Again, is coming from my innovation because nobody believed on us that the human red blood cell also has some of the microRNA, because they are coming from the progenitor cells, and progenitor cells are filled with the microRNA. Why do they lose? They lose what? They lose mitochondria. Red blood cells, they lose mitochondria. They lose the nucleus during course of the differentiation, but they retain some of the microRNA. So we exploited those microRNA, and we saw their interaction, those microRNA interaction with the parasite target protein, and by blocking them, first we identify the interaction, and then we block that interaction to the vaccine. So this is that story. And then this is a like a tubulin I said, from that or microRNA screen, we also found the tubulins are the very, very important targets for human malaria parasite, because they are not only helping in the today Professor Gulal discussed the spindle formation, its segregation, but they are also involved in the dendrocytogenesis in case of malaria parasite. So we also thought of this venturing to that area. We could first establish the tubulin dynamics. We express the tubulin, establish tubulin dynamics, then we screen some of the malaria pathogen box compound from medicines for malaria venture, and we could show that they are there. Not only that, we also do a lot of work on red blood cell proteins, their modification, and this is for the first time only we in the field of red cell biology could show that there is a palmitylation process happens in the human red blood cells. So palmitylation is just like addition of the palmitylation moiety to the protein, and by addition of this moiety to the protein, it makes it more going to the membrane, anchoring to the membrane, and that can make the protein to be there in the cytoskeletal structure to have a proper cytoskeletal will maintain for the integrity of the red blood cell. So it's a very simple question, but it has lot of impact because red blood cell is a very flexible cell, and in that case dynamicity is very much important. So palmitylation dynamicity we analyze, and then again we target it. So finally we have a palmitylation inhibitor, which is a good anti-malarial, but it is targeting through the host. This is just very much very short story, but took a lot of time, 3 years for research, where we all know that artemisinin forms the free radical, and that is leading to the anti-malarial or any anti-proliferative effect of this artemisinin, and in that case we know the artemisinin has an endoperoxide bond, and that is in the presence of iron only, this endoperoxide bond gets activated to active drug. So that means what is important? The important is iron. Of course artemisinin is also there. So when the artemisinin is there in the human malaria parasite, the iron is coming from the parasite, the free iron. It was very simple logic that let's provide the iron. When we are providing the artemisinin, let's fortify it with the iron. But directly iron addition was not a good idea, because we wanted to really liberate that iron at the time of action of artemisinin. So we encapsulated that with the iron nanoparticle, and then in that case this was the preparation. Again, it's from my chemistry collaborator, and then we could make the iron nanoparticle, and thus we characterize the iron nanoparticles. They are released in the pH dependent manner. Again, why pH dependent manner? Because the artemisinin has to be acted in the food vacuole, and there the pH is low. I wanted that iron should be released in the lower pH when the artemisinin is there, and with those rationale we could make, and we could show we can enhance 10 times the artemisinin activity by just fortifying it with the iron nanoparticle. We also tested that in an animal malaria model, and we could show yes, they are very efficacious, and then we could also, this was published in Lancet, and we also got the award for this. But the new story is coming up where we are using the RTBT formulation long Husn. That is nothing but this iron. So we are just talking to AIMS hospital, where we are asking them, can we really take the artesunate which is already drugged, and then the long Husn which is already there in the with the preparation, can we combine it and can we have some. Then we also made some artemisinin derivatives. Then we also showed that derivatives are good for artemisinin resistant parasite, because the parasites they are also evolving. Then we could also show not only why they are becoming resistant, autophagy mechanism being introduced, and then we could show the autophagy machinery is also being dropped. Very recent paper which is really being covered by NEJL. This paper is published in AAC, where I could show there is an upregulation of cyclophilin in the artemisinin resistant parasite, and when I target that cyclophilin, we can have an and then finally this compound is an isosporine compound being already used for hepatitis B, but now I'm proposing it for anti-malaria. So it is a replication. So that's it. And very, very new event where I have shown the 4-carbon sugar as a like a candy, which I propose to give to the kids. They can really do in addition to the artemisinin chemotherapy treatment. These 4-carbon sugar, which we diabetic patients generally they take. But very recent, 10 days back, there was a paper which says this erythritol is not good for heart, but that amount is very different. We are proposing in a very safe dose, and but it has to be used with it. But also, we did some. I come from Chhattisgarh, where the malaria is being treated by the antibiotic, and you will be really surprised. So I just analyzed those ant venom, and I could find some anti-malaria effect. And then I also interact with some Nigerian because they are the most affected country and the isolated some phytomedicine. We have a media report, we have a media report.
Thank you, Dr. Sharda. That was excellent, and we really have gone through, I think, a journey of not many years. We have gone into your work and wonderful papers, and the kind of confidence you had in your beliefs that people that microorganisms may not be there, but you are believing that, and you have come up with some very good targets and the therapeutics also along with that, like the CO1 and the CO2. I believe that these targets and these therapeutics in the future will be very good intervention and eliminating this malaria. So I believe that this is something very good work which may have elicited a lot of questions also from the audience. Any questions that you're welcome to ask
I hope it was not too much.
but I believe that because I'm also working on we work on the purposing of drug-resistant bacteria. So is this your C1, C2 compounds FDA approved?
So this is the computer guided synthesis process and this that. But the Japanese codeine is totally purpose. So I also work on the purposing where they got hepatitis B. Now I'm coming out one of the paper is already in press where we have shown that this antidiarrheal drug that is also anti-malaria now.
I could see some of your repurposed drugs.
Sir, in this I have not shown this one is hepatitis.
Yeah, this one.
Yeah, so this is not an immunosuppressant. It's different than that cyclosporine. Like cyclosporine has a lot of trouble because it is an immunosuppressive drug, but it has been made from the cyclosporine A. It's already there in the FDA approved and in the clinical trial for hepatitis B. So we are exploiting this drug for now.
So you do some combination recent trial about this artificial intelligence combined with
yeah. So I applied to go to Oxford. Unfortunately, I was not selected. They might not find me that suitable. So I wanted to do this AI, artificial intelligence in drug discovery, where I wanted to see how the target space is being covered through whatever library, and it would be a very good idea. So I applied.
believe that because now we are working and we are having collaboration with the AI people who design peptides for us. Yes,
so I should talk to you.
But already you have done so much. It's a great
Yes, sir. I think I needed training in one direction, but I would love to learn.
So lastly, I will say that what is the vaccine scenario?
For malaria? Yeah. So as we know that the vaccine which is being developed for the USP, antigen CSP, RTBT, that is only showing the 43% efficacy. But still it is there, 43% protection is also good enough when we are talking about the kids, children are involved. But again, vaccine, because of the polymorphic nature of malaria parasite protein, success will be limited, as I say, but again, last 3 months back there was a report that the mRNA vaccine also being prepared for malaria vaccine. But again, as I say, the drug was the solution. We know the famous chloroquine, we also know the famous artemisinin. So I believe that of course that research should go on, but through the drug discovery we can have this.
So we really appreciate that this is a great wonderful work and we have been it's very nice to
All credit goes to my student actually. They are all the time on their toes. We are really having such a great team. Every time they make me very much hard to work very hard for them. So I also make them very yeah. So it's a mutual relation which we are having. Thank you. Yes, ma'am. Yes, ma'am. Yes. Ma'am, like packaging like phospholipases, there are 2 things in malaria acid. Yes, ma'am. But the one which is expressed in the blood stage, as I said, there is a multi-stage process: fever stage, blood stage, lymphocyte stage, and the mosquito stage. I am targeting the blood stage because the exit process I can do better. Like experimentally, I have a technical limitation. I don't grow the hepatocyte and liver stage because I don't have mosquito facility. So I am targeting the blood stage packaging like phospholipases. Yes, ma'am, but it is very different. Only 22% similarity. Yes, ma'am. So it is only 22% similarity, only into the phospholipase, some motifs. But it's entirely like a plant because we have one advantage, the parasite is a plant like. So that's what the advantage is, we can target specifically. Yes, ma'am. Yes.
Is there any relation between the infection and the blood group? Because in the over time as well, there were some studies showing that specifically O blood group is less getting infection. And if they are getting infection, that is less severe as compared to the other blood groups. Is there something in the malaria as well? And if it is so, how we can intensify that protection against the parasite?
So as I told you that blood group antigens very faintly correlated with the infection, total infection of malaria parasite. In case of malaria parasite infection, I am totally focusing on. So the blood groups are not that much important to play a role. However, some of the blood group antigens, they work as a receptor. If they will work as a receptor for parasite interaction, of course they are going to have some impact. Like a Duffy, we know that Duffy blood group is very much important for Vivex interaction, right? But now we are also knowing that the parasite invades Duffy independent way, Duffy dependent way. Then, so that's what I am saying. Yes, it has some role, some correlation can be obtained, but not on a very sole based. Yes. And I am also working on some of the blood group antigen like a Ken. So I took the human progenitor cells, did the CRISPR-Cas, eliminated that antigen and asked the question what happens to infection, only 50% block. Maybe then parasite will adopt without that antigen. So that's the problem.
Dr. Ma'am.
Yes.
First of all, thanks a lot for giving such a wide information. And my question is that is glutathione defense system of liver work against the sporozoites or not?
Okay, yeah, so glutathione mechanism is not only for liver stage but even for malaria stage, like as I said, ROS mechanism in general has lot many role for parasite infection, establishment of infection and proliferation. For example, even artesunate effectivity is directly correlated with this ROS mechanism. Like if you are blocking that ROS system and you are not allowing more ROS to be formed even after addition of the artesunate or not. Like for example, malaria parasite, what it does? It takes the hemoglobin in case of blood stage. In the liver stage, it is taking other nutrients and all. And during that course of metabolism, it also forms the lot many reactive oxygen species. And that has to be handled by either the ROS mechanism of the host or parasite itself has some. So that's what this is again a very, very good target. If we can combine the defense mechanism, ROS defense mechanism, as well as the artemisinin film. So in that case, you are blocking the defense mechanism, you are putting more pressure in terms of ROS, and then combining can give us synergism. And we are also doing that. Again, I'm sorry because every space I am really ventured on. So we are working with the nitrofluorine compounds. Right? They form also, they interact with the ROS system, glutathione mechanism also, and that is leading to more ROS, and I am combining it with nitrofluorine. Again, I said the purpose that because nitrofluorine is a urinary tract infection UTI. So yes, nitrofluorines are toxic. That's what. But you know, like 2 months back, I started this work 2 months back. I suffered from UTI, and then doctor gave me either go for antibiotic or go for nitrofluorine. I was reading and I found wow, this is a good ROS drug. And in that case, toxicity is there, but still it's the over-the-counter drug. Yeah, NF is the over-the-counter drug. So we also tested that with the artesunate. So the dose, what I was prescribed for the malaria. So the dose is, I think, I don't remember exactly, but 2 tablets morning and evening was the dose. Yeah, it comes under NF. Yeah, I don't remember that. It was the same tablet I tested for malaria. Yes.
Recently, CCRS developed a medicine IU-62 as an anti-malaria drug.
Yes.
What is the reliability of this drug? Because it used totally herbal product, and they are telling that it is a best anti-malaria medicine available in India right now.
Actually, I have been approached by them to have the scientific rationale of that. Because still there is no scientific rationale, like why this combination of herbal products are anti-malarial in nature. So we need to really do it. I don't have the answer right now, but of course the target can be identified, question can be asked, what is the metabolism, what's the impact on the fetal metabolism of the process. So I've been contacted by them to have the scientific rationale for this herbal preparation, but I thought too many things in that preparation. My whole life will go on that, so better. Yes.
I think most of the questions have been answered, and we are hugely thanking Sharina for this answer. Thank you again. Our next speaker is.
Thank you, Professor Singh, for a very interesting talk. I would now invite Professor Prince Sharma to kindly present Professor Singh with the token of appreciation. I would now request our chair, Professor Sharma, to kindly introduce second speaker.
Okay, our next speaker is Professor Ahsan Ali from the Institute of Nanoscience and Technology in Bali. Professor Ahsan Ali is located in effort in understanding the electronic structure and magnetic properties of molecules, materials, solids, biomaterials, and interfaces. One of the major activities he is involved with is the designing of organic molecular magnets and single molecular magnets, improving their magnetic properties for suitable applications. His research interests have been ab initio investigation of molecular magnetism, interface nanomagnetism, molecular spintronics, magnetostructural dynamics of biomolecular systems, and I think so on. He's been to many things actually, and he has published about 66 papers in this area. He has won patent also to his credit. He has been a visiting professor to Uppsala University. He has been a postdoc also from there in Uppsala University, and currently he is associate professor in the Institute of Nanoscience and Technology in Mohali. So we welcome him and we are inviting him for his talk, please.
Yeah, thank you, Professor Sharma, for this introduction. And first of all, I would like to thank the organizer, especially my collaborator and friend, Dr. Avni, for inviting me and giving an opportunity to talk about what we are doing recently in our laboratory at Institute of Nanoscience and Technology. So this is one of the youngest institute of Department of Science and Technology, and it is located not very far, only 10 kilometers from here. It is located in Mohali, and we have a very young and vibrant atmosphere there, and we just only provide the PhD, purely research institute, and our students get degree from ISER Mohali. So I would like to invite all of you to our institute, and we have really a very nice and state-of-art facility as well as a beautiful campus as well. Okay, so today I'm going to talk about few things that the previous speaker was talking about. Sergio has given a very nice introduction for the malaria in to tell the story that we are doing. Three things we are going to talk first, that the activation process of artemisinin, how does it get activated, and then how that artemisinin involved in the drug resistance, and the last story will be the stimulatory effect on drug activity, especially for the artemisinin. Now it needless to introduce again that how big is the problem. Malaria is 1/3 of the global population is under the threat of malaria, and it's a deadly disease. In every day around 1,800 people die because of this malaria, and the challenges are there. It's not only the health rate, it's also impact that socio-economical aspect in global scenario. And major thing that Sergio was talking about, that we have so many things to prevent it, but scientifically we have progressed very little to combat this disease, especially like creating the new medicine or effective medicine, and we don't have understanding also that existing medicine what is there today. And we are going to talk that part only. So there are two different kinds of drugs that are available. One is quinine based, the other one is artemisinin based. So the quinine based drug, it hinders the formation of the hemoglobin, which is known as malaria pigment. I'll talk about a little more that. And the other one is the artemisinin based, which has an endoperoxide bond, and endoperoxide bond, it gets disrupted and it kills the malaria parasite. Okay. So what exactly the malaria parasite does? So for survival, metabolism, and for reproduction, it needs food, and that their food is that hemoglobin. So hemoglobin has two perks. One is the heme perk and one is the iron porphyrin. So it basically and it forms the beta hematine. That means the two protoporphyrin combine together and for the beta hematine, and that goes for the biocrystallization and it gives the hemoglobin. And the chloroquinone, what it does, the moment it oxidizes, chloroquinone comes and binds with this. So it prevents that beta hematine formation. So that this perk is a completely irreversible process. So that means that once it forms the beta hematine, so that hemoglobin is permanently damaged. It cannot be converted in the body. So this is a very dangerous process, but chloroquinone binds with this. And the other mechanism is that artemisinin. Artemisinin actually has endoperoxide, this oxygen-oxygen bond. Now it breaks and it forms the radicals. And once it forms the radical, it becomes very reactive, and then it again interacts with the cell wall, breaks the cell wall, and that's how the parasite dies. So in both, their mechanisms are different, but at the end, both of them do the same thing, that killing the parasite. Okay, and what our question is that there is a lot of controversy there with the activation of RTBT. So at the beginning in 1985, it was proposed that the thermal decomposition leads to the homolytic cleavage of the endoperoxide bond. So what is homolytic cleavage? Like just scissoring the oxygen-oxygen bond, and it will generate two radical center. This is okay. This was at the beginning proposition, and then later on there are several experiments come with where the iron, as also again since I was talking about this, that iron play an important role for the breaking of this endoperoxide bond. And recently, few other experiments are showing that it is homolytic cleavage of this endoperoxide bond is more feasible. So, as a computational scientist, we wanted to take this issue and try to find out computationally, like we will see and try to find out what exactly is going on here, because that experimental debate is still around. Okay, so this is what I was talking about, that iron breaks this oxygen-oxygen bond and then it creates one radical center. Okay, but if this oxygen-oxygen bond homolysis happens and there will be two radical centers, and experimentally both reports are available. That sometimes it gets down like it creates monoradical, sometimes it's biradical. Okay, so this is the mechanism. The homolytic cleavage will see that two radical centers, and for monoradical mechanism it will have one radical center and one anion, because it is already getting one electron extra. And to study this, we have performed the ab initio thermodynamics. What we did that this is we calculated the free energy of activation. Activation means that breaking of the oxygen-oxygen bond in either way, two radical mechanism or one radical mechanism. And to do this, there is a challenge here, because we are adding one electron here. So to calculate the density, we have to have an isoelectronic approach. So in that case, we consider that iron protoporphyrin as a source of the additional electrons that will come into the Artemis. Now, here, what we are observing here look that we studied both in the gas phase as well as in the solvent phase. Now, if you look that this biradical approach both in the gas phase and solvent phase are lower in energy compared to the monorail. Okay, so this is really a good understanding of this case. Although the energy difference is not much, but what it indicates that this homoelectric cleavage for the endoperoxide for breaking of endoperoxide bond is quite feasible, and that's what we have concluded in this paper. And then we also find out that how reaction propagates. So like once this bond, endoperoxide bond breaks, so the two radicals will be in the oxygen center, but these are very highly reactive. So what it does, it sees the hydrogen atom of nearby carbon, and it happens that one free and one pole rearrangement of the hydrogen atom, and this we found that these two other structures, it is quite stable. So the once once the radical form, it immediately goes to the hydrogen CP arrangement through this particular two radical center, because in two radical centers there one is in oxygen radical center, the other one is on top of the carbon, and that's what we also energetically found. These two are quite lower in energy. Okay, so this part, what we concluded that this is quite possible for the activation of artemisinin, and it is even lower in energy than one electron reaction. And last year we published this article, and now we move to that the artemisin's drug resistance thing. So it has been observed that Cas13 protein has been associated with the drug resistance for artemisinin, and in this article by IRA in 2014, they have identified 4 mutant protein of Cas13, and it is observed that Y493 and C582Y are the most affected protein. In that case, the artemisinin, if the mutation is there, then artemisinin will not act as a drug over there. So this is the general that Cas13 domain experimentally people have synthesized and reported. It has the 2 domains. One is that Cas domain, which is very symmetrical and conjugate one, and the other one is the BTB domain. And then all these 4 mutations are basically in the Cas domain. Okay, so and they propose the mechanism in wild type protein, because of this Cas domain binding the substrate for the ubiquitination process, and it caused that degradation of the substrate. But now if you have the mutation in the Cas domain, so this binding process doesn't occur, and which increases the substrate in the blood, and that causes the drug resistance for the artemisinin. So we here address that. So what are the difference of the protein dynamics with all the 4 mutant structure and wild type structure? So looking into the protein dynamics, we wanted to understand that how the mutated protein are behaving, and how it could be correlated with the drug resistance of the artemisinin. Now, so this is the standard procedure. How do we perform the simulation? We take the protein and we save the code. We need to use water molecules surrounding the protein in a cubic box, and for that we need to use the water potential, and first we minimize the structure, equilibrate, and then we create the production dynamics. For around 20 nanometers, 200 nanoseconds. So what we do basically is that we leave the protein to move as per its dynamics in the experimental or biological condition, and then we loop the protein behavior, statistical behavior, how we are behaving, and that's what we do in molecular dynamics simulation. And with statistical average we get the thing. So one of the things we get is the RMSD, that how proteins are moving over the time, and we compare the RMSD. So here we have three domains, primary domains. One is the Cal's domain, which is quite conserved, and then we have the loop region, and then we have the B2B domain. Now in all the cases, you see that Cal's domain are not fluctuating much, and this is what is kind of surprising to us, because all the mutations are located only in this particular Cal's domain. But when you see the dynamics, that it is not changing in the Cal's domain, rather it is changing in the overall dynamics of the protein. And more change we see in the Y493. If you look into the RMSD plot, so you can see that the protein is moving in one fashion, and then suddenly it is jumping, and then again another jump. So the more prominent effect is happening in the Y493 overall structure dynamics. And what is the implication of that? I'll talk in the later slide. But not only that Y493 we see, we also see that C582I also has the larger dynamical change in the protein because of this particular mutation. Okay. Now, if we look at RNA fluctuation, again we see that the mutations are in this particular region, but the protein dynamics is again same for all the cases. But what we change in that B2B domain, not in the entirely B2B domain, only residual 370 to 390, which is the loop region of the domain. So the things are changing in the loop region of the domain. And another more interesting thing we observed that in Y493H mutation, the protein is fluctuating a lot. The largest fluctuation we observe with the phase change of the protein for this particular Y493. But if I look into the overall protein, that radius of gyration, so what we observe that this only this particular protein, the mutation, mutated protein is quite close in structure. The reason is that the wild type tyrosine, that this particular bond was quite long, 7.8 angstrom, but after the mutation, so that histidine and that 426 glutamic acid, that this oxygen and hydrogen bond is quite stronger, and that's why the protein is becoming like restricted, closer, but it is having larger dynamics, and that dynamics is not spreading all over the protein. It is only going through the transferring to the B2B domain. Okay, and then we also see that what is the impact of this secondary structure for this change of the dynamics. So the wild type, if you see that more, you can see this particular around loop region. The structure is mainly dominated by trans and alpha helix, but for Y493 it changes from turn to from alpha helix to 310 helix and quad. So it's not only changing the dynamics of the protein, the secondary structure of the protein is also changing because of this in the wild type. So whenever they are fluctuating in a particular manner, and if they are highly correlated, then it is one, and if they are anti-correlated, means that one is going up, the other will go down. This is also a correlation, but in that case, that is we call that anti-correlation. So the correlation and anti-correlation of the wild-type protein is large. The moment we put that any mutation, this correlation pattern breaks. Okay, now what we are concluding from this work that because of the mutation, the BTB domain fluctuation increases, right? So that BTB domain fluctuation increases. That means that the ubiquitination process, the BTB and choline binding will get affected. Okay, so the originally proposition was there that this gas domain and the substrate binding will hamper. Not only the substrate binding will hamper, we also find that this choline and BTB domain interaction is going to change, and that is the reason that how mutation affect the drug resistance for RTBT. Okay, so and this also we published last year. Now I will talk another interesting work that artemisinin. So if you see that what is the structure of the artemisinin, you will anonymously see this particular structure, because this is the only structure, crystal structure is available for the artemisinin. Now I'll tell very other facts that if this particular structure of the artemisinin, it's quite possible to synthesize also. Now, when you talk about the drug, the synthetic artemisinin drug, but so far there is no synthetic drug available. So this synthetic artemisinin we cannot use as a drug. So what we use so far as a drug is a plant extract from this Artemisia annual plant. So we extract that artemisinin from that particular drug. Now, so this is something that if we know the structure of the drug, then why we cannot use that synthetic drug. But anyway, so we were working some different other projects, and then what we realized that this chemical structure has 6 stereoisomers. Now, if it has the 6 stereoisomers, so basically it will have total 64 stereoisomers. Okay, and what we know synthetically, it is only 1. Now it automatically questions that whether the activation of this particularly synthesized one is quite feasible or not. And again, then we started looking into the literature that what people are missing, or what we are missing basically, that we are claiming that in principle there should be 64 artemisinin, but only 1 reported. And we looked into the recent literature, and in 2018 and 2021 there are 3 more structure reported. So we are quite confident that in the coming years, out of 64, many more will be known. Anyway, so what we did, we took all the 64 structures and then calculated their stability of all the 64 structures, and the first one is the synthesized one that we have taken, and we calculated the activation energy, that how much energy is required to activate the drug. Now, if you see these 2 figures, it is quite obvious that the crystal structure has stability, but to activate the crystal structure so that it can act as the antimalarial drug, it is not possible. It has quite high activation energy. And then we looked forward all, and then we found these are the 2, and Okay, so we generally put a cutoff up to 15 and we look in more details that those are the isomers that could be effective as a drug. So when we use as a synthetic artemisinin as a drug, it doesn't work. But when you take it from the plant extraction, it works because the plant extraction, we don't know that how many different artemisinins are there. So this is why we are quite confident that these two particular drug isomer will definitely going to work as this as the effective drug for the artemisinin. And we also realize one thing, that why these two specific structures are acting as a drug. So what we see that we have this hydrogen bound to this particular carbon, and this forms the hydrogen bond with the endoperoxide. Now when it forms the hydrogen bond, so this endoperoxide bond becomes elongated. So when the bond is elongated, then you need less energy to break it. But if this hydrogen bond is not there, then oxygen-oxygen bond form quite a strong bond, and it needs more energy to break this. And this is what we have observed, and we are proposing that these are the stereoisomers which are going to have the lower energy for the activation energy, and out of this only two is the lowest in energy. Okay, with this we conclude this that we obtain the effective drug isomers for the artemisinin. Okay, and yeah, so what we observed there is that the artemisinin, the endoperoxide bond is quite important for the activation of the drug. Now, what happens that drug inefficacy happens because if the drug is activated oxide, like the drug has to go to the food vacuole of the peroxide, and then it has to be activated. Right. Now, if you are taking the medicine and somewhere in the stomach or in the blood that endoperoxide bond is getting activated, then it is not going to kill the malaria. So, kind of resistance or inefficacy of the drug is going to happen. So, we are proposing one thing that that nano drug delivery, many people are working on this too. So, we put that SBS micellin, and we put that drug within the SBS and DPC micellin, and what we observed that both of the micellin can take the drug within the course, and then we can efficiently deliver it. But in comparison to SBS and DPC, we found that DPC is better because it stays within the core system. Okay. So with this, I'd like to conclude this before we talk about that alternative possibility, the biological mechanism of alternative possibility, and we also understand that how protein dynamics is changing with the mutation, and that is associated with the drug resistance, and identification of the stereoisomers that are going to have the better efficacy of the artemisinin drug, and how to encapsulate to prevent that off-site activation of artemisinin. And I'd like to thank the students, and here mainly I'm going to talk about Sister Grace, who is going to present a poster tomorrow, a poster number 106. So I'd like to invite all of you to our poster. And before I say thank you to all, I'd just like to advertise that we are hiring people to work on this similar computational project. So we should trying to spread these. Thank you for your attention.
Thank you, Dr. Esnali. This was an excellent work on a lot of work on the CEO chemistry of RTBT, and I believe that people have gone through this work and they may have some questions. Any questions are there? Yes, obviously from Dr. Chandra.
Very nice one. I really enjoyed your talk.
Thank you.
So I have two questions. First one, as you said, some mutation in the French domain is impacting to your domain.
Yes.
Yeah. So in that case, and then you said the fueling interaction.
Yeah.
Colin interaction to that is being different now.
Yeah.
So have you done that simulation?
No. So that is like we are planning.
Yeah.
We have started. We are planning. That is more interesting. Is going to be actually.
That will give you more insight.
Yeah. So
that
is
your hypothesis is that the interaction occurs.
So, but we could show that the dynamics of that B2B domain is quite high, quite strong. And that is, if something is fluctuating a lot, then it is very less likely to bind with the substrate or that choline protein. Yeah, but still we need to have the real evidence. And this was the thing that Weaver was also like quite interested to.
I was not the reviewer. Yeah, and then second thing in your stereo chemistry. So there you are saying the two form which you think is active one.
And we are not telling the two form. The two form has the lowest one, and another 10 to 15 we found those are lowest one, but definitely not the crystal structure. So the crystal structure you can discard it as that it is not a drug at all. So people so far was trying to synthesize the crystal structure and try to use as a drug, and they failed. And why they failed, now we have a reason that why they failed.
Understood. So my question to you is that the two form which you think can be activated with a very low energy?
Very low energy, yes.
So do you really think that for activation of drug has this much impact?
Yeah, of course, definitely. Like it's all about the game of the activated. Even if the drug is there, if it is not activated, then it will be there with the substrate itself.
But you said it's a change in the energy, not yes or no. Is this a yes or no situation or?
No, if your activation energy is quite high, then you have to provide that much of energy, then only it will break, right? So.
But in other form also they will get activated. They might require more energy.
More energy.
But they will activate.
Yeah, so if they activate, then it will act as a drug.
Yeah.
So now it is the question that how easily you are able to activate it. So if you are able to easily activate, that is going to be the more efficient.
My third question is
Yes.
So there you are saying that
yeah, so I don't know how it is going to release over there, but this is but a very preliminary thought, I will say that, because as we say that if premature activation is going to affect the drug application, right? So how to prevent that? So this is what we are just trying to see that whether within the mycelium it is going to be stable or not. So those kind of study we are doing.
Sir, I have a very small query to you. The background is of what you said in the beginning, that there are certain drugs which you synthesize in your lab. And then you can similarly extract them as a active component from an extract. Do you think they would work exactly similar?
No, if it is the same molecule, if I could identify the molecule, which particular molecule is acting as a drug, then it should work similarly.
But we have many papers where they say like beta hydrogen, when you extract it from a plant or you synthesize it, they don't work the same way.
No, so that's what my point is that when we are extracting from the plant, we don't have any exact knowledge that what are the simple modification plant has done in all those cases. So the plant extraction is always work better than what human has synthesized. But what I'm trying to say that if we can properly understand that which particular molecule, what modification is there in that plant extract, and if we can get this idea, it should work similarly.
Is it easy to do that?
No, it's not easy. That's why it has not been done, and that's why we are computationally trying to do it, because for us it is easy to design, but for the experimentalists it is really a very tough job to consider all this variation.
Very good work.
Thank you, ma'am. Yeah, so right now, yes, so that's why we have to have an experimentalist counterpart on this. So right now what we did that we have prepared a minimum model where we can construct the micellin, and that is around 65 DPC molecule we have taken, and we inserted the RTBT within that, and then we check the stability, and it is quite stable. But experimentally all those things we have to collaborate on. Yes. Right.
And that structure determined which you are talking about?
Yeah, so that whenever you synthesize, you end up almost only one particular structure.
Yes.
Yeah. So yes. So and that was the misleading part of this work actually so far. So that stereochemistry part was never focused, and recently it has been like people have tried to people have found experimentally the different isomer as well, and theoretically it is possible 64.
So, and actually in the reverse direction I have also questioned it. So in that structure where you spoke about Y2, that is tyrosine to histidine mutation,
And yes.
structurally they are very different when you looked at them. The properties of the two amino acids are also very
Right.
different. So that was the environment is changing. Did you actually look at the environment from one end to the other, or was it solvated? Because when you're talking about changing its direction or changing its conformation over there, it can also be because of the property of that amino acid to which it is mutated and the surrounding residue.
No, the surprisingly thing is that is not the case here. So we also thought that when mutation is there, so larger difference in the dynamics between the wild type and the mutated one will see exactly at the same position. Okay, so if you see here, this is the BTB domain, and you cannot distinguish much that they are quite similar. But if you go to the BTB domain, that the dynamics is much distinguishable, much more distinguishable in the BTB domain. So what we try to understand is basically the allosterate effect of the protein. So you change in one place, but the effect you see somewhere else. Yeah.
there is quite a fact.
I want to discuss with you.
I can see people fidgeting out there for lunch. So if you can excuse me, ma'am, later on.
Okay.
I would like to conclude, and probably your lunch will be intermittently by questions also, because I have been now getting instructions that okay, the lunch is ready. So please, if you can have your questions for him in the lunch session, I would be happy. And you are very happy to answer this question. So once again, thank you so much, Dr.
Thank you.
For this wonderful talk.
Probably somebody from his lab was trying to destroy other drawing in the middle. How did this happen?
Lecture, you all this in the last. You can discuss.
Yeah.
Thank you, sir, for the nice talk. I would now invite Professor Sharma to kindly present Professor
मैं थोड़ा ज़्यादा कम बोल रहा हूँ। हाँ बोलिए, एक मिनट होल्ड रखो।
Today, 23rd March, marks the martyrdom day of Shaheed Bhagat Singh. Bhagat Singh was a prominent revolutionary and freedom fighter who played a significant role in India's struggle for independence from the British rule. He dedicated his life to the cause of India's independence. Born on 28 September 1907, he was deeply influenced by the ideas of socialism, communism, and believed in the power of masses to overthrow colonial rule. He was just 23 years old when he was hanged by the British for his role in the Lahore conspiracy case. But his legacy continues to inspire generations of Indians. His commitment, courage, and unwavering determination continue to serve as inspiration to all those who aspire for a better and a more just society. His famous slogan, Inqilab Zindabad and Sarfaroshi Ki Tamanna, still resonate with people of India. Today, on his martyrdom day, we all remember him and he remains alive in our hearts. And before we conclude, I would like to invite Professor Ashwini Paul to kindly present the chair, Professor Prince Sharma, with the token of appreciation.
Thank you. Thank you so much.
I would now request the participants to kindly go for the lunch.
प्रेजेंटेशन क्लोज करना क्लोज और कुछ नहीं करना कॉपी होता है आ नहीं सकता
This pathway was fungal specific. Okay, so that was one thing. And it was also a cytosolic pathway. So this was actually the first non-cytosolic glutathione, or first cytosolic glutathione degradation pathway that was actually discovered some years ago. And this is basically the detailed characterization of this enzyme complex. So this is actually, so this is the second step of the DUG1 peptidase. We again characterized it and showed that the DUG1 peptidase actually was forming a dimer, cleaving cisglycine to give you cysteine plus glycine, and actually it was a conserved dipeptidase, but it was also found in humans. And the human the enzyme CNGP2 carnosine non-specific dipeptidase, we showed that actually the homolog CNGP2 actually is a cisglypeptidase, very similar to that one, right? So that was the characterization of that pathway. But what we found out very soon, shortly after that, we discovered two new pathways. One we call the CHAC1 and the other one was CHAC2. So the name is kind of strange, it comes from E. coli. But essentially these are very conserved proteins found across from bacteria to man, and it's a different kind of enzyme. It's a completely different kind of enzyme. So these are gamma glutamate cyclotransferase. So there's a large superfamily of gamma glutamate cyclotransferase, to which CHAC-C is one subfamily, and the function of these enzymes were not known. Okay, so we actually were able to identify the function of CHAC1 and characterize it, and then we did CHAC2 subsequently in some years later. And the interesting thing is that this enzyme cleaves glutathione again, but instead of giving glutamate, it gives you 5-oxyproline and cisglyc. And then, of course, cisglyc can be acted on the DUG1, whereas 5-oxyproline, which is actually cyclic glutamate, can be cleaved by oxyprolinase to give you glutamate, right? So this was a completely new discovery, and interesting was that this was found from bacteria to man, and it was surprising that so many thousands of papers published on glutathione, and people have missed it in researchers in humans have missed this very interesting protein, very important protein. So the rest of my talk is actually going to be on this protein, that's the CHAC1. And some interesting features about CHAC1, I'm just summarizing a lot of work here. Essentially, the CHAC1, unlike, for example, the DUG pathway or the known gamma glutamate transcriptase pathway, it can only act on reduced glutathione. I told you that there are two forms of glutathione, reduced and oxidized in the cell, and whereas the other enzymes, gamma glutamate transcriptase and the DUG pathway, can act on both reduced and oxidized, CHAC1 can only act on the reduced form, so it doesn't act on this. Second point is that it's highly upstream of the integrated stress response. And here we're talking about mammalian cells, so it's a highly upstream of the integrated stress response. So basically there's an integrated stress response pathway in mammalian cells, and which have got multiple triggers, and downstream of that there is a lot of cascade of genes getting upregulated, and one of them actually is CHAC1. And the other thing is that CHAC1 is also a very active protein, it's very highly potent, it's highly induced during stress, and then it very rapidly comes down, and it also has very good activity compared to, for example, its homologue, the CHAC2 protein, right? So we found this quite interesting. Of course, very, very interesting. We thought, this, and particularly this property of acting on reduced glutamine was oxidized, because that suggested that it can change the redox environment of the cell, and therefore it could be some kind of a signaling molecule, right? So that's what we try to investigate next. Cytosolic glutamine degradation by CHAC2 could it be a cellular mechanism for altering redox? We did a lot of work with yeast, and I'm not going to mention again that because there's no time for that. But I'm going to go straight into our work with the zebrafish model. So essentially, before that, just to tell you that it's well known that reactive oxygen species at high levels, of course, cause damage to proteins and DNA, and therefore are toxic and have to be removed. But at low levels, it's also well known that this is actually a signaling molecule, right? So the question is that what we were asking is that could glutamine degradation by CHAC1, could it, for example, degrade reduced glutamine, which we know that degrades reduced glutamine potentially, lead to an imbalance of GS and GSSG sufficiently so that it changes the redox environment, and then there could be some downstream consequences of signaling. And we were looking at calcium. So actually we did this in yeast, these experiments, a whole set of experiments in yeast, which I'm not describing, and we showed that actually when you overexpress CHAC1 in yeast, you can actually get calcium signaling, and some of the channels are, the TRP type channels and the L-type channels are activated. So I'm not getting into that because there's no time for that, but I'm going to just talk to you about what we've done with the zebrafish work. And so, essentially, just like the humans, which have got two proteins, the CHAC1 and the CHAC2, zebrafish also has two proteins, CHAC1 and zebrafish CHAC1 and CHAC2. And essentially, so if you just see this data here, for example, this is just a control plane, so you can see that this is the human CHAC1 is this one. You can see that, so this is a bioassay where if that enzyme is active, it will grow on the plates, on glutamine plates. So this is active, so it's allowing it to grow. This is the zebrafish CHAC1, you can see it again allowing to grow. When the protein is active, enzyme is functional, and this is an active site mutation of the zebrafish CHAC1, and you can see it's not doing it. So this is CHAC2, which is very weak growth, so you can see it's much very lower activity than the CHAC1 protein. So clearly there was a functional proteins over there. So the question is, does it can it change the redox, for example? So what we did was, we actually we did these experiments in yeast before actually going to zebrafish. So what we did was, first of all, if you overexpress zebrafish CHAC1 in yeast, what happens to the glutamine levels? Okay, so now here look at it, for example. So these are cells where glutamine biosynthesis is continuing, right? So when you have continuous glutamine biosynthesis, even if you have some glutamine degradation, the levels will not fall. And you can see that indeed this is of course the vector control, and this is the active site mutation, which is the like the vector. So you can see with overexpression of the zebrafish CHAC1, it leads to about 50 to 55% fall in the glutamine levels. So fall in glutamine levels is there, but not that substantial. Right? But the most important thing was to look at the redox state, because we wanted to know whether the expression of the zebrafish CHAC1 can lead to change in the zero redox state. So we used what is called an ROGFP2, which is a GFP2, it's a green fluorescent protein, which is it has been constructed such that it responds to redox. It's called the ROGFP2, and you can see that in the white type cell, this is the oxidative state. Whereas if you express the zebrafish CHAC1, you can see that there's a much more oxidized state. So that suggested, preliminary evidence from yeast that yes, the cells the enzyme can change the redox state of cells. So we were then, of course, important. It was next, So the important thing then is what about in zebrafish itself? Okay, and we knew that zebrafish was CHAC1 induced development. So was there a signaling role for CHAC1 during development? Right. So we thought we would investigate that. So this is just a sort of summary view of the expression profile of zebrafish CHAC1. You can see that it's expressed very early on in life, so the dark signals you can see, and it's expressed in the myotome or the developing muscle. It's expressed in the brain, it's expressed in the heart and the lens. So you see, this is the myotome developing muscle. You see there the brain, midbrain, hindbrain, the retina, and there's also the heart. So you can see that these are where predominantly CHAC1 expressed. Okay? And then, so then we also, and when we look at what happens if you knock it down. So we use what's called are oligonucleotides, modified oligonucleotides that can knock down that particular gene. So we do that, and you can see that the fish zebrafish actually is not happy, right? And actually it leads to embryonic lethality. So actually you can see that in 72 hours virtually with all fish actually died. Right? But if we capture the fish earlier and we try to see where exactly which organs are being affected, you can see that the organs affected were brain, myotome, and the heart. So for example, if you look at here, for example, you can see that midbrain hydrogen boundary, the white type cells, you can see that the clear boundary you can see here. So you can see in the knockdown morphins, you can see this boundary is missing. It's more clearly visible here. So you can see a clear boundary here, whereas here this boundary is missing. And these can be restored if you put back the wild type JAK1, right? So basically the rescue is also possible. And this is again the myotome, the muscle, developing muscle. You can see that this is the wild type, and you can see this the morphin. And here you can see the heart, for example. You can see that in the morphin where you have a JAK1 knockdown, you can see it's a very striated, long heart, and with called pericardial edema. Whereas the normal heart is actually much more sort of globular in shape as compared to this one, right? And if you look at, for example, the heart pumping functionality of the heart, you can see that. So you can see that this figure shows you, the heart pumping and the wild type pumping very nicely. Whereas if you see that, you can see that much lower pumping. So functionally also, not just in strength and shape, but in functionality also, the JAK1 knockdowns are actually defective in heart. So essentially, that was interesting because then we found some interesting evidence that literature that basically these tissues where we were seeing JAK1 expression and the organs which were also not also affected, that they were also important for calcium. For example, calcium, these papers, calcium signals drive cell shape changes during zebrafish midbrain hindbrain boundary, visualization of calcium signaling during embryonic skeletal muscle formation, vertebrates, again zebrafish study. And again, calcium exclusion is critical for cardiac morphogenesis and rhythm embryonic zebrafish. So there was a very interesting correlation between JAK1 expression patterns, JAK1 knockdown phenotypes, and calcium roles. Okay. So the obvious question was there a link? Could we establish a more direct link, right? So what we did was we first of all need to establish whether we showed in a yeast cell if you express it you can see a change in redox, but what about in the developing zebrafish itself, right? So what we do is we use this GRX1 ROGFP2 probe and we inject it into the cells, and then we have a wild type and the wild type with a knockout, and then we look at the live imaging and we track the changes, right? And so just to sort of summarize this data here, essentially in the JAK1 morphin, and this is the quantitative data. So basically in the JAK1 knockdown, so this is the wild type. So wild type is more oxidized, is less oxidizing, whereas this is so wild type is more oxidizing because the JAK1 is expressed, whereas the knockdown doesn't show any change in redox. And here again in different types, 10 hours and 20 hours. And this is, I think, looking at midbrain hindbrain region where we looked at the next strip and then we quantitated that way. So clearly there was a change in the redox potential, okay, as we have seen and we expected. And then so we thought, okay, so if that is there, then do we also see a change in the calcium levels? And what we did was we used this receptor GCAM6S, which is a calcium inhibitor, and then we did that, injected that, and we did it with the morphine also. And then we found, of course, it's known that we don't get signals very early on with this particular program, but at 20 hours and later, you can see this is the wild type. You can see the green fluorescence coming up, and the position is changing here. Whereas in the wild type, in the morphine, you can see there's no change in calcium. And this is again the quantitation. Similarly, this is in the midbrain hindbrain region. You can see that there is a change in the fluorescence here, but there is virtually no change in the morphine. If you look at, so this is like again, look at the envelope layer. So this is again, if you just look, so this is the wild type, and you just need to watch the borders, the envelope layer. You will see green flashes coming up, right? And in the wild type, whereas you will not see anything, no changes in the mutant, right? So you can see, so this is the left panel here. If you look carefully, you can see the green flashes coming up. Here. You can see many green flashes coming up. And whereas in the morphine, there's actually no change in it at all. So basically, what we could observe, therefore, was that actually there was a clear change in calcium signaling as well. So therefore, what we sort of concluded from this was that so redox is a new upstream activity of calcium releasing development, and so it's well known that there are many upstream regulators of calcium release development, NADP, cyclic APRs, IP3, which can trigger the different L-type, TRP type, and binary receptor channels and lead to downstream signaling and development. But what we are saying and proposing here is that there is a new upstream signaling of which we call redox, and that is actually initiated by the checkpoint protein. Alright. So that's doing development. But what about in adult cells? So here, we also in mammalian cells and adult cells also, of course. So in developing cells, CHAC1 has a very important role, and if you knock it down, it's lethal. But once an adult is grown, then if you knock down CHAC1, it's not lethal anymore. And but it's very important. And we find that there are many cancers where CHAC1 is regulated. And so we thought maybe we should try and find an inhibitor of CHAC1, because we thought that might be interesting for us. So we said let's try it. Of course, we're not something which is new for us. So if you look at inhibitors, there are essentially two types of categories. There is what is called a first-in-class, whereas that means it's the first such molecule ever discovered against this particular protein, or the best-in-class, where for example, many drug targets, there are many drugs already known, and the idea is to get better drugs and better drugs and better drugs, right? But CHAC1 actually falls in the difficult class is actually the first-in-class. You don't have any starting point, and CHAC1 actually falls in this category. So we thought anyway, despite being difficult, let us see if we can get into this field. Although it's not an area that we are very experienced with. And so the idea was essentially, could this be a new approach to tackle ROS in cells? So basically, it's well known that many groups around the world, and even there's some of these cosmetic companies like L'Oreal, etc. They actually try to increase glutathione levels in cells, and they do it by actually activating the biosynthesis. NRF2 is a well-known transcription factor that activates biosynthesis of many of the enzymes involved in glutathione biosynthesis. So that's the normal strategy. There's other approaches to actually increase transport by using glutathione esters and analogs or precursors. But what we are saying is actually this maybe inhibition of degradation would be a novel way to actually identify new inhibitors that can enhance glutathione levels. So essentially inhibition of transport CHAC1 is a potential novel way to enhance DSL level. So that was the sort of the thought process that we had. But for that we need to actually have CHAC1 structure, and at that time CHAC1 structure was not known, so we have to start with that. But then the problem with CHAC1 is it tends to aggregate, the purified CHAC1 tends to aggregate, and the first is all the structure, still a section of the law. So what we've done is we made mutants that don't aggregate, and we are trying to crystallize that in collaboration. But what we did was we activated solve the CHAC2 structure which doesn't aggregate, and then in collaboration with colleagues in Intech, we actually solved the structure of CHAC2. So with that structure, so with this, can we use this CHAC2 structure to then find inhibitors of CHAC1? And so basically the two approaches which we thought was, one was to take an approach where you take a virtual screen approach for model structures. So basically we have the CHAC2 structure, so model the CHAC1 on that, then do an active site mapping to further sort of define the active site, and then do a virtual screening for in silico component libraries. And the other approach, of course, to develop a cell-based assay, a high-throughput assay where you can completely screen completely new compounds and then subject it to subsequent modifications, etc. So I'm just going to quickly tell you what we're trying to do with, for example, with the first approach. We've of course modeled the structure. At that time, also the alpha-4 model also came out, and we compared that, and we used both of those structures. So I think then we did a screen using the Schrodinger software glide. And then we were able to screen from lakhs of compounds to come down to about 100 hits, and based on that, we then took the best 9 hits, and we procured them. We purchased these from Molport, and then we subjected this to an in vitro assay, because we got these leads and then we can check whether it actually works in vitro. So we also had developed an in vitro assay for this enzyme, where what we do is we take CHAC1 and we treat it where we add glutathione. It degrades it, and then we add a coupled assay, so the DUG1 enzyme is also added, and then we get cysteine, and in acidic ninhydrin you can get a pink color. So using that we can assay, and when we did this assay, what we found was, of course, the inhibitor should not act on drug 1, it has to be so that control has to be done. But what happened was, when we did this assay, we found that none of the substrate, the best hits that we got actually were actually of any value at all. There was virtually no inhibition, and these were at 100 micromolar levels, which is actually quite high. Then we started thinking about it, and what we realized that actually that the substrate of care of glutathione for the substrate of CHAC1 for the substrate is very high. It's about 2 millimolar. And so what we think is that basically the high KM of CHAC1, which is about 2 millimolar for glutathione, will make active site inhibition very difficult, because any inhibitor you need it actually at micromolar or less low level, but then it will be very, very difficult for it to compete with the CHAC1 with the glutathione substrate. So what we think we need is actually non-active site inhibitors, maybe like allosteric inhibitors, etc., which we are now sort of working on that direction. And the next few minutes, what I'll do is I'll just tell you what we've done in the other assay. So basically the other thing is when we are trying to develop a cell-based assay for chemical screening, because since it's a first-in-class series, we think we'll actually have to screen large chemical libraries, and I don't think too much hope on that on the virtual screening. So we have to screen large libraries and then try and get some lead which we can then work back there. So what we've done is we've actually developed two screens. One is screen 1, and the presence of CHAC1 inhibitor permits growth. So what we do is we have a lead cell, and we engineer it in such a way that when we add glutathione, basically it grows. But yeah, so the presence of, but if you have CHAC1, so this requires glutathione to grow. But if you have CHAC1, it degrades glutathione, so the cell stops growing. So the cell will stop growing. So if you have a CHAC1 inhibitor, then it will grow. Okay? So this is the screen we developed, and we also deleted the multi-drug resistant pumps of the strain for the effective for drug screening. And you can see, so it has a Z-trans, very good Z-trans score, which is a very important statistical parameter for high throughput cell assays. Then we also developed another screen where we make the presence of CHAC1 inhibitor prevent cell growth. So basically here what happens is the glutathione is added and it used as a sulfur source. So if you don't have CHAC1, it doesn't get degraded, it don't get the sulfur source, right? So this is another assay where if you don't have CHAC1, you don't get growth. If you have CHAC1, you get growth. So again, so there were two parallel assays, and so we did a nitrofugal assay, and we found that they were both screens very robust and reliable as seen to the Z-trans scores, and so these were the Z-trans scores at 40 hours. So I think that they are very, very good screens. It could be very, very powerful screens for us to use. So with those we set up. Now the problem is getting these libraries are very expensive, extremely expensive. So we got one which was available at Himtech. And we have a TICANS robotic system in our institute. And this spectrum library, which is only 2,000 compounds, but we got that from Himtech. Somebody gifted it to us, and we thought, okay, let us screen this these 2,000 compounds at 100 microliters. So with that, we screened it, and so this is the data here quickly. So the negative control is like this. So this is the screen 1 only, and when you read that data, and the screen 2. And the positive control is like this. So basically, so we found several hits, and there were some very, very high hits, which are those of colored compounds, so that's why giving good body. So you can see there were 5 or 6 hits here. So I think that this particular library had two compounds. One was glutathione, one was oxidized glutathione. So they also showed up as hits because glutathione will support growth in the first screen. So those were actually, in a sense, it validated the screen, but then it was no use to us. So these 6 hits we are sort of looking at are preliminary suggest. So these are the colored compounds which were not true when they were up, very high OD because they were colored. So this is a visual screen OD. And these are the compounds which we are actually looking at. Preliminary indication is that maybe they're not very good indicators of CHAC1. Still, so I'll end here now with that. And so essentially we are now trying to get more libraries. The only libraries are very expensive, so we're trying to reach out to collaborators and colleagues who can help us, because we think we have a nice assay system set up, and it's a completely novel enzyme and potentially may be very, very good. So we are taking it forward. So what can we conclude about our attempt to do with the discovery? One is we think that with the high KM, which is something which we didn't realize in the beginning, in silico screening for active site inhibitors are likely to work for allosteric inhibitors we identified. So we're looking at approaches where we can do that. Leads identified till now being followed up in nucleoacids, so that's what we're doing right now. Being a search for first-in-class compound, more compound need to screen and sell the data. So these compounds are extremely expensive, and we are talking to multiple companies and people and colleagues from across the world to see if they will be willing to collaborate with us on this. So let me end by sort of thanking Mr. Work and who is now a postdoc. However, he's did work with the zebrafish in collaboration with colleagues who was adventurous enough to get into zebrafish work. Shraddha is the one who's doing all these inhibitor studies right now on high-fructose process screening, etc. And setting up, although we have a robotic system in the institute for 10 years, she's the first one who actually set up this robotic system for drug screening. It's been used for other things, but nobody's been using for drug screening. So also this was a major effort for her side. And so these are others who have been involved in the initial drug pathway and the CHAC1 identification. They've all graduated, some are faculty now. And the collaborator Chinmoy Chaudhary, who was in PGI, Inspire Fellow, she helped us in the virtual screening and getting the model of the CHAC1 model based on the CHAC2 structure. Kartikeyan, who was collaborating with us on the CHAC2 structure, crystallization from Imtech, and Rajesh Ramchandran, my colleague from ICER, who is a zebrafish expert, and he collaborated with us in helping us on those zebrafish. So I think with that I'll end, and I'll end here. Thank you very much.
Thank you for wonderful talk. Now session is open for questions.
Yes,
please.
Good afternoon,
Yeah.
sir. It's been wonderful to see you.
Right.
It's been wonderful to see you.
Okay.
For the past 2 years, I have been chasing you.
Oh, I didn't know that. Okay.
Finally, I met you here.
Okay.
Sir, I have a question. How can we relate CHAC1 to the stem cells? As you told us, CHAC1 did its best in zebrafish. But why is it not so in humans? As it is leading to the formation of the skeletal muscles or the heart cells with the usage of the CHAC1.
Yeah. Yes, yeah.
So why it is so contrasting or so robust in nature?
No. Actually, in mammalian cells and mouse also, it leads it's embryonically lethal. So in mouse also, so humans of course, so in mouse also it's embryonically lethal, and there also the muscles and all are affected. So people are not, see, it's not easy to do so many, So zebrafish is a good model for if you want to look at, if you want to take it, catch the embryo, because it's embryonically lethal in zebrafish, but if you catch it a little earlier, you can actually see where the defect is lying. So in mouse also, it's embryonically lethal actually. So it is the same, the phenotype actually is the same. It's just that in adult cells, once the cells mature, so even in zebrafish, if I take a mature zebrafish cell and if I knock out CHAC1, probably nothing will happen. So in adult cells, human cells also, if you take adult cells, nothing happens in the knockout. It's only during development that it's lethal. Okay, so I think it's going to be the same in both in mouse and so at least in mouse is there. So we are now, one of my master students is actually looking at CHAC1 SNPs to see because to see if there's some correlation with the gene, etc. So that's the bottom line. There is a strong correlation between what we see in zebrafish and mammalian cells. Okay.
Thank you very much.
Now I request Professor Rajiv to take over the
the authority.
I hope you won't mind if I call you only Dr. Abdul, because I found your name very easy.
That's fine.
Dr. Abdul is an assistant professor at the Center of Biomedical Engineering and Joint Facility in the Department of Metallurgy and Material Engineering. He has key interest in designing and developing of biomedical systems, processing technologies, and implantable medical devices with clinical applications, orthopedic sports, medicine and diabetic food healing. He has 2 filed US patents and a strong ongoing research associated with the various departments at Tata Memorial Centre Mumbai, AGIM of Chandigarh, MS Rama Memorial Hospital Bengaluru. As an assistant professor with joint appointment at Center for Biomedical Engineering, Department of Metallurgy and Material Engineering at IIT Roper, is working on setting up one of its kind multi-material biomanufacturing facility to indigenously develop and manufacture implantable medical devices. I welcome you and request you to start here.
Thank you. So, good afternoon to everyone. Contrary to Anandji's work, mine is very applied, so it will give a very distinct, a very different flavor. And what I'll do is, I'll start by explaining the title, Tissue-Derived Biomaterials for Reconstructive and Therapeutic Applications. So, the area of tissue processing and use in medical devices is very, very new within the country. In fact, if you are aware, the recent medical device regulations of 2017 implemented from 2018 have a provision for using human tissue as part of medical devices. So that completely changes the paradigm for how we approach regenerative medicine in a clinical sense, with an aspect of technology translation and commercialization. So my lab basically addresses 3 of these essential challenges, or I would say opportunities. One is in the area of chronic wounds. So if you look at the numbers, they are quite large in each of the 3 I will mention. 40 million patients suffer from chronic wounds. Typically these are diabetics. A limb is amputated every 30 seconds. In India, the prevalence is around 4.5 by 1000, although data is sparse, but those are the numbers that we have that are reported. And approximately 45,000 amputations a year. The recurrence rate of the chronic ulcers, because of various factors, is around 60 to 70%. So it's a major healthcare challenge. The number of diabetics in the country is growing. Diabetes also has an implication of bone health and bone fracture. If we look at the second case, which is bone fracture, largely in the area of orthopedics, the applications lie in orthopedics and sport medicine. There's a recent report in the Lancet which states that there are around 455 million cases of bone fracture annually. This was in 2019. So you're looking at roughly 500 million per annum. And traditionally the way of fixation has been using hardware, metallic hardware. So we are working in that area using tissue-derived materials to address that challenge in part. And the third area, which I won't get into because it's not under the ambit of this presentation, is AMR. We are doing some very interesting work there. And if anyone is interested, they can get in touch with me separately. So just for the students out here, when we are looking at the development and commercialization or translation of biomaterials, it is challenging largely because it is multidisciplinary. When you look at the life cycle of the product, the conception all the way through to the patient or the clinician's hands, it involves a number of due diligence that needs to be done. And this is the typical approach we carry out in the lab. It starts with a problem statement. We have clinical collaborators, so all
the work that you will see is in collaboration with clinicians who come up with a problem statement. It has to have a large scale of opportunity which I described. And then the nature of experiments and studies we do are at the lab scale, where we are looking at materials processing. So in this case it is processing of tissue. Principally we look at two tissues, the placental tissue and bone tissue, and either combination of those with synthetics, their evaluation in vitro, benchtop testing, pre-clinical testing, and then of course it goes down through to the clinic. And one largely overlooked factor is this portion here, which is how do you make them in bulk. You know, the whole essence of translation is that you have to be able to manufacture, and you have to be able to manufacture cost effectively because it has to serve a large population. So we also tie up with several manufacturers in the supply chain for sourcing raw materials, right, and to evaluate the feasibility of production at a large scale. So this is essentially what we do. Our core competence lies here, but yes, the clinicians and manufacturers are also involved. So we see that what is developed in the lab can hopefully one day be taken to the patient. So the first area of application that we look at is chronic wounds. So in short, chronic wounds are basically those that have not healed for 12 weeks or more. Okay. So around 3 months, if they have not healed. Mostly these are seen in diabetics, type 2 diabetics. They have a number of other comorbid conditions, infection, exudate formation, right, that are associated with the site of the wound. And so to address this, to address the reconstruction, regeneration of chronic wounds, we are looking at placental tissue, in particular the amnion. So those, I'm sure everyone here is familiar with the placenta. In India, we have a large challenge of tissue wastage, right? So every time there is a delivery, the placenta is discarded. We'll see every time there is a hip replacement, which in India is happening in, or a knee replacement, total knee, the bone is discarded. So the essence of the group is that how can we take this wastage, what is essentially wastage as of today, and utilize that as an extracellular matrix at scale to promote the healing of these chronic wounds. So the placental structure, if you look at it, the innermost layer, the layer in contact with the fetus, is the amnion. Amnion is a very thin layer, only few hundred microns at best, on an average 100 microns thick, and it has 3 layers. In itself, the topmost layer is the epithelium, the cellular layer. Then there is the basement membrane, and then these 3 layers combined give it the measure of its bulk. It is structurally similar to skin, and importantly, it is a cocktail of regenerative factors. So at a small scale, amnion has been used sporadically since the 20th century, early 20th century. In 1997, it was approved for use by the US FDA, and since then there have been a number of clinical studies. Of course, the challenge when you are working with human tissue is it is hard to get, and there are ethical concerns. So scaling up has to be done in partnership with an agency that has the requisite protocols and the requisite licenses. So we are working with the leading tissue banks of the country. The first tissue bank is Tata Memorial. I've known them for a long time now. They supply us with the placental tissue, and all the work that you see here has been done in partnership with Tata Memorial Bank. The genesis I will explain behind this whole idea of using tissue was that during my training as a PhD and postdoc, in the orthopedic sector, there were a large number of products that were coming out from leading companies, Medtronic, Stryker, Wright Medical, and these were essentially in the area of singular growth factors. So I'm sure you have heard of bone morphogenic protein, PDGF, VEGF, and the strategy then was that these could be made recombinant in a recombinant fashion and injected to create an efficacious situation in vivo. However, over the last decade, the use of these singular growth factors has significantly subsided, largely because of the side effects they demonstrate. right? So the rationale is, why can we not use the matrix as a whole, which we know has a number of factors in physiological concentrations, process it in a way so that the factors efficacy is maintained as compared to the native tissue, and then use graft from one patient and implant it in another patient. So that has issues, which is why you need to process. But traditionally how this has been done is, in the clinic, doctors don't have an idea of how proteins behave, the material science behind proteins, and so this challenge we thought we can take up pretty well, use tissue, process it, and hence come up with relevant medical devices. Now we are thankfully supported by the regulations also. So the step here is that we procure fresh amnion, which basically is the innermost layer. It is stripped off from the chorion, which is the underlying layer, and we remove all the cells using a concoction of decellularizing agents. These are essentially non-ionic surfactants. Typically ionic surfactants like SDS disrupt the calcium linkages. I know it happens in bone, it happens in other tissues also. But a key focus of the group is to ensure that the processing does not hamper the physical and the biochemical properties of the tissue, because essentially that is what you want to retain prior to implantation. And the ready availability of the tissue means that it has to be preserved at room temperature. Normally tissues are kept at -80 for long periods, but in India that is not a sustainable approach. So one has to be able to store these at a retail outlet, or in a room at room temperature for several months or a couple of years maybe. So we look at lyophilization. However, lyophilization essentially is dehydration of the tissue, right? So we are doing lyophilization along with a lyopreservant. It's a disaccharide known as trehalose. So this approach we have essentially evaluated using raw tissue from TMC to see if there is any impact, adverse impact of the processing on the tissue structure and material properties. So here we see the histology of the membrane. These are the different conditions. The first is the fresh amnion. Very clearly you see the epithelial layer and the spongy layer. This is the trehalose treated, which you see has become bulky, lyophilized. This is decellularized, which because of the lack of these cells has significantly reduced in thickness, and then it gains some bulk on trehalose treatment. But the idea is that for the most part the features of the structure are preserved. Electron microscopy shows that even the topography has been retained when we follow the decellularization and the disaccharide treatment prior to lyophilization. Now processed amnion is applied, it can be applied in various forms. Typically it's applied as a layer over the chronic wound, and if you ever have had a wound which is more than a cut and you have had a dressing placed, you'll observe that there is a certain amount of exudate or fluid that is released from the wound surface. The layer that is in contact with the wound has to be able to manage that fluid, right? So there has to be a transmission of vapor from the surface of the skin through to the atmosphere, and that is evaluated using the moisture vapor transmission rate. So again, this standard we brought in to the amnion. This was not done prior, but this is common in the medical devices industry. Unfortunately, in India, we don't have a setup where we can evaluate medical dressings. So in the process of this work, we have created the setup and the ability and the know-how to be able to characterize any medical dressing. So you will see that when we evaluate the vapor transmission rate, it lies ballpark within 2000 to 4000 grams per square meter per day, and that is in the range of several commercially available dressings that you see. Then we evaluated the mechanical properties, in particular the tensile strength and the percent elongation, to see if and how the processing methods essentially affect the strength and the strain of the processed tissue. Now the range that you see from 2 to 10 MPa is again similar to human skin, alright. And we did assessments of surface wettability Essentially, the tissue that is being implanted needs to be hydrophilic, so it is able to attach to the wound surface. And very positively in the T, if you see the TLT, wherever there is T, there is Trehalose, and there is a good amount of hydrophilicity that was observed. In fact, it is very hydrophilic, completely changes from the fresh decellularized or the fresh cellular membrane. So in fact, we see that this preservation is actually improving the applicability, clinical applicability of the membrane. We did basic spectroscopic evaluation to see again, are there any marked changes or differences amongst the process groups vis-a-vis the fresh amnion that was observed. What we were looking for was to see if there is any changes in the collagen structure. So for that we looked at circular dichroism, and fortunately we see that the helical structure has been preserved in the process of the treatment. Furthermore, all the groups that you see, the lipids, the amide groups, you see the presence of a saccharide in the Trehalose one, right? Ribose, deoxyribose from the DNA, various peaks have been mapped, and so we are able to show that both decellularization and lyophilization together do not adversely impact. In fact, Trehalose tends to enhance the mechanical and the wettability properties of the tissue. Again, we did some assessment here. Bradford assay, total soluble content, hydroxyproline assay for collagen, and then we looked at glycosaminoglycans to look at the whether there is any depletion of these essential molecules from the matrix, and we see in a large part that there isn't. Right. The problem has been that decellularization, use of surfactants significantly depletes the organic content, and that is not what we were hoping to see. Now, this process basically can be used for other layers, including skin. Of course, it will have to be tailored. But the idea is that once you have processed a tissue, you can combine it with other materials to create a medical device depending on the nature of the application. So you have this lyophilized amnion, you can pulverize it so you get a powder, and this is what we have done. I'll show you some of the products we have developed. You can add some excipients, create a bio ink which can be used as a gel. It can be 3D printed or injected into various shapes and forms. Right? So in a way, the processed tissue or the placental tissue becomes a platform for making a number of devices depending on the clinical indication under consideration. So as an outcome of this roughly 2 years of work now, we have a product which is, so this is the technology readiness level. For those who are not familiar, it is the extent to which the development has happened, post which you can commercialize. So this can basically now be used in patients if it is at 8, 9. And then at different other levels we have micronized powder, we have an amnion-based gel. Amnion-based drops are used for ocular indication, grafts are also used for ocular indication. In fact, in India, the greatest usage of amnion is for corneal transplants. And then if we combine the amnion formulation with it, again, this dressing that you see, the foam-based dressing has been formulated, it's been prepared in the lab. We have scaled it up with the partnership of a large foam manufacturer. So everything is indigenously developed and done. And then you can see some of these 3D printed materials. You can combine layers, you can integrate the synthetic with the bioactive. The key aspect here in the bioactivity is the tissue processing. Right? So the platform is the tissue, you can change the formulations and then you can integrate it with products. Okay, so that was the first part. There's another project that we are working on. Again, this involves tissue, but this will be bone tissue. It will address the challenge of fracture fixation. So another invention we have in the lab is an adhesive, basically a glue that can stick pieces of bone together and pieces of wet bone. Now adhesives for skin and soft tissue have been prevalent. Fibrin glue is almost routinely used. Cyanoacrylates are used by plastic surgeons. But when you're looking at bone as a material, bone is a composite of a ceramic, which is apatite or calcium phosphate, and largely collagen. So you combine that with fat, lipids, blood, various other fluid elements, it becomes very hard to glue them together, right? So actually the student that has done this, Simar, is sitting here. She's a PMRF fellow. So that is her work. And so we have this adhesive, but can we give the adhesive a certain amount of bioactivity, right? So like we look at placental tissue, for the application of bone, we look at bone tissue. Now in India, there's been a surge of total hip and total knee replacements. It's massive. If you look at a large hospital, if you look at say Max, Saket is the largest. There you will see around 2,500 knee and hip replacement surgeries per annum. If you go to Shalby, which is globally the largest, their center in Ahmedabad, that will give you around 12,000 joint replacements, largely knee they have, per annum. And typically these have to be revised 15, 20 years depending on the physiology of the individual. The challenge comes when there is a revision hip or a revision knee, because typically that is accompanied by bone loss. Okay, and so far we have not faced it, so most of us aren't aware, but I'm sure in the next 5 or 10 years you will see a surge in the number of secondary hip or secondary knee surgeries. Now when there is a bone loss, there has to be a substitute that is used to replace or augment the structure, and that is typically a bone substitute. So the adhesive, and the addition of the activity, through the use of this, the bone graft is a means to solve that. Now as these surgeries happen, naturally, like the placenta is wasted, the bone is also wasted. So in a total hip replacement, the femoral head is basically excised, it's replaced with an implant, the stem and then the head, and the tissue goes waste, right? So that again is a significant amount of tissue that can be processed, and its bioactivity can be used along with synthetics to come up with some very advanced products. All these are important. Just to give you an indication back to where we were, instead of the placental grafts, plastic surgeons commonly use a product of Integra Life Sciences, right? So 10 by 10 sheet, 10 centimeters by 10 centimeters is around 1.5 to 1.75 lakh rupees. Okay, it is massive. So therefore you can see, even the demineralized bone and allograft that we get is all important. Okay, so there's some good opportunity here, and the field is only growing. Again, this is a schematic from the Lancet. So you'll see that from age 70 onwards, there is a significant increase. On the right side is males. When younger, males tend to sustain more bone fractures, but as we age, the number of women sustaining fractures increases because of osteoporosis, postmenopausal. Amongst these fractures, the color codes are a bit nuanced, but if you look at it carefully, the fracture of the hip and fracture of the femur account for the largest share. Okay, so say you have a fracture and you have hardware supplementing or used for fracture reduction. An application of an adhesive basically would be to augment the hardware. Okay, or you have a case where there is multiple pieces that are formed in the fracture, or a fracture at the joint where the anatomy of the reconstruction becomes very important. Okay, that is where you would use an adhesive to essentially restore and reconstruct the joint. So this is a video showing. So this is Simar there. She's trying to pull up. So this is a paste essentially. It's a paste which sets at room temperature, and it's very hard to pull apart. She has to torque it. She has to really torque it and twist it to basically get it released. So this is the orthopedic surgeons are quite excited about this because it can sort of really change the way they reduce fractures. So that's a video of the product. Okay, talk a bit about this. Essentially, if you break down bone into its constituents, yes, there are a lot of growth factors, but the design approach that we take is more holistic in nature. We look at a calcium phosphate base, where essentially the hydroxyapatite is formed using multiple CAP constituents. Then here comes the tissue-derived additives to imbue the bioactivity, right? And tissue comprises collagen type 1, various non-collagenous proteins, osteocalcin, collagen, so on and so forth, which are contained in demineralized bone, phosphorylated serine and citrate, which you find in tissue but can also supplement externally. And then there's a liquid phase. So after I describe this, I'll go to how the cement is made. But this demineralized bone here, which you see this image on the right, again it's like a white powder. The idea is that you take the mineral out, you take bone as a tissue, you treat it in an acid. Okay, and that's where a lot of clinicians go wrong, because this technology has not changed in 30 years. It has not changed in 30 years. But naturally, if you subject a tissue to concentrated hydrochloric acid, there's going to be some damage to the organic content. Okay, so we are looking at new ways of processing this tissue, removing the mineral, and essentially coming up with a demineralized matrix, which comprises these proteins and collagen and so on and so forth, right? Which can be added to the cement. So the cement preparation involves mixing the solid phase, which is the calcium phosphate and tissue additive, along with the liquid. You get a sort of putty like M-seal, and that putty will set in a few minutes. Okay, clinically, if it has to be used, it has to set within 12 minutes or so. Okay, if you are 3D printing it, you have to delay the setting time to several minutes, maybe half an hour, 45 minutes. So you are able to play around with the property of the material based on the end use you are looking at. If you take a look at these images, this forms a very smooth paste-like structure. So this is the adhesive cement. This is been a very brittle. It breaks. It's calcium phosphate. Doesn't have this kind of flowability. Okay. I'll not go through all the testing we have done. Just to show that we have used various combinations of the adhesive component, the tissue, the calcium phosphate. And then it has to be evaluated mechanically. We have done some compression testing, and broadly when we compare it with the native cement, it's around 15 to 20 times the compressive strength. So it is significantly stronger in compression also. And then again, this becomes a platform for development of further products, right? So we have a 3D bioprinter. In fact, this has been upgraded. We have a dual head 3D bioprinter now. Where you can sort of use two different materials and different patterns, and this is the cement being printed, a different formulation of the cement, which can then be used to create 3D structures, right? So whereas in the first case the tissue was the platform, here we are using the tissue as an additive, but yes, differing combinations of the tissue and synthetic materials, okay, allow for a lot of value addition for the clinician, and that's exactly what we are trying to do. I would like to thank these PhD students. Shatrupa Sarkar, her work is on the placental grafts. She is a Prime Minister's Research Fellow. Simar here, again, is on the orthopedics. Jahin is a polymer engineer, plastics engineer, a brilliant chemist. So he does all the synthesis work, making the synthetic dressing, so on and so forth. Everything in the synthetic domain is his work. A couple of grants pertinent to this work. And then clinical collaborators at Tata Memorial Center. These are my principal collaborators, Dr. Tarush Gupta and Sandeep Patel from plastic surgery and orthopedics at PGI Chandigarh. Thank you.
Dr. I get the privilege of asking you the first question.
Please go ahead, sir.
Throughout your talk, although it was very impressive, one question which kept on revolving in my head was about its immunological tolerance.
Yeah.
You did not speak anything on
Yes,
that.
yes,
Could you
yes.
please comment on
Sure,
that?
sure.
Because that is the main.
Yes, absolutely, absolutely. So, when you look at a tissue, naturally the goal, there are different ways of reducing the immunogenicity. Okay. Typically, how it has been done so far is that a piece of bone will be taken, it will be stored in the deep freezer for 6 months, and then surgeons will use it, and they will see a certain rate of success. There will be some inflammation, maybe not. Right. Lyophilization again reduces the immunogenicity. And most importantly, what I didn't talk of is prior to implantation, you have to terminally sterilize any implant. So that is done using gamma irradiation. So these are well tested in the medical devices domain, and yes, that is how it is done at multiple levels.
So according to you, the rejection rate is zero.
It is very minimal. I mean, surgeons are very comfortable using these drugs. There is no rejection. That is why it is. That is why you have to process it. If I take it from you and some patient A and put it in patient B immediately, then yes. But the reason it is processed is to reduce that and to extract the bioactive factor.
My worry was that when you use it for a diabetic foot, there is so much of respiration. And when you put in any organic material there, I think it is very difficult to completely make it.
Actually, it doesn't invoke, I think, the immune response.
Yeah, amnion will not. Amnion is immunoprivileged.
Hybridization cannot kill antibodies.
Amnion is immunoprivileged. Amnion will not invoke it.
I think so. Has to say something.
But bone will. Yeah.
I think you overplayed in the.
Please go ahead.
Sorry to say that.
That's fine.
You said like amniotic dry thing is used for cardiac transplant, if I hear correctly.
Amnion grafts.
No, so there is a difference. You making this powdered amnion, right?
You misinterpreted or misheard. I am saying amnion membrane grafts.
Membrane
have been used by
after lyophilization, right? You processed it, you 3D printed it. And
No, not 3D printed. The graft is without any processing. A graft basically is the tissue which is taken, it is minimally processed. And that structure.
I work on the cornea.
Right. So the graft is, I'm not talking about 3D printing there, it's only the graft.
So that's not used for cornea transplant.
It is, sir.
Where can you give?
I will give you numerous sources. LV Prasad, Narayan Netralaya. Okay. They also make graft.
Can you tell me the three name people of LV Prasad? They are all my students.
No. Names.
Nasu, I know who is doing it, and Vivek Singh and LV Prasad.
Sir,
they are not using. So let me explain. It's they're not using for the cornea transplant. Cornea transplant is very different than this using the amniotic. They are using amniotic membrane just when there is a severe burn. They apply it, and that's not a transplant.
No, so what they are currently doing, these fellows, how they use it is what you are saying is correct in a way. They take the limbal cells. Okay? They cellularize.
I understand.
Yes. So I didn't explain that.
I invited them in ISA meeting.
That
they just showed the allogenic and all that.
Yeah.
And that is completely different what you said.
No.
What you presented here.
No. So it can be used as a substitute for cornea.
No.
But
that's not true. Not in human death.
No, but in LV Prasad or in Narayan, what they do and what has been routinely practiced.
Okay, who do you know in Narayan? I work with Narayan all the time.
This SAS is in Bangalore.
Yes.
Sir. Yeah. It's
who is the director?
Devashish. No. Director, I know the person who runs the tissue bank.
Devashish doesn't work in Narayan.
He works in. He's in Bangalore. Anyway, that's off the point, sir. That's off the point, sir.
What I'm saying, that's when you present these things, you have to be careful what you talk.
No, but you thought I'm talking of 3D printed grafts for eye. No, I said tissue grafts. So 3D printed are not grafts.
Use the cornea transplant, yeah.
3D printed are not grafts. Grafts are.
I understand.
Yes, so that you are wrong there, respectfully. So therefore, I interact with them. I interact with several surgeons, including ophthalmologists at Max, and I will counter your point, sir.
Yeah. So it's the research director in the Narayan Netralaya is Alka Ghosh. Devashish is not here.
Alka Ghosh I have also spoken to. I have not corresponded.
He is my postdoc. He did a postdoc with me for 2 years.
Okay, sir.
And he is doing gene therapy. He is a researcher and Rohit Shetty, who is the...
Sir, knowing names is one thing, actually interacting with surgeons is something else.
You name it, they all, you go and see all the publications.
Okay, yeah, thank you.
No, but I would suggest you are a young scientist, and what I want to tell you, not any argument, with all due respect to you.
I think that would have been a better start.
Yeah. So it's just be careful what you present. Don't try to overclaim being.
No, I'm not overclaiming anything, sir.
Okay, that's fine.
Yeah.
Sir, we are really impressed.
Thank you.
And such type of discussions are taken in a very healthy way.
Yeah, no.
I think we all teach.
These are professional discussions, sir. But I have my own, surgeons,
that's all right.
which I interact with, and I get inputs from them. So I'm going to present what I know and what I have interacted. And surgeons, the clinical community. The clinical community, someone may agree, someone may disagree. That's how it works.
That's not true. If you have it, you should put the name of those people who you work with. It's you have to show that you need to have like some professional. There's some professional,
Sir, there's also startup involved. We have 2 grants with the startup, that's all proprietary. A lot of things I cannot share on.
That's fine.
So so we can discuss in person though, if you want.
Such scintillating. Just a minute. I would request each one of you to keep the tempers down. And let's discuss things in a very healthy way.
Yes.
And not discuss human beings or their names or... I also don't remember.
Yeah, that is not productive.
So no, please, don't. My humble request is that let's speak only scientific things here. And we could be different in our approach. We could have a different thought process. That is what science is. If all of us start agreeing with each other, then what is the point of having a conference? So, but at the same time, maintaining the record. I'm sorry for these words. Thank you. Please go ahead.
From what?
Any alternate,
Okay.
not generate any immunological reaction.
No, amnion is immunoprivileged. But even then it is sterilized and terminally sterilized.
Sterilized doesn't mean that it will not.
No. But gamma irradiation.
Sterilized is disinfected basically.
No. I understand. I know what it. But it is a routine practice in any kind of grafting process, and it has been routinely done. So typically, when you take a graft, if you want to preserve it, okay, you dehydrate it and you sterilize it. Now that reduces the immunogenicity. There may be instances, but surgeons, orthopedic surgeons, dentists use a lot of bone graft. They are comfortable using allograft. They use synthetic materials. I will tell you, leading orthopedician of the country is trained on the orthopedic, and I am on very good terms with him. He will say, if today you give me a third, you give me an allograft, I will stop using synthetics. So it's opinion. No, so that you can increase. That's why I said I have not presented. We have also done shear testing. We have increased the number of samples. The point was not to show, again you'll have to look at standard deviation. Roughly is around 15%, 15 times increase. But that sample size will be increased, and the goal was to show the combinations you can. It's a material design part of it, right? How you prototype it?
Sir, actually I work on fish scale biomaterials and same like hydroxyapatite and collagen we get.
Okay.
But then again I submit that reviewers really ask for MTT and all results like for antimicrobial results. So I think so we need to validate, being a biologist and you being an engineer scientist, we need to understand each other. And sometimes we don't know, when we started working on that we were not very familiar with FTIRs and all. But then when we start working, there is a lot of things before it is marketed. I want my product to come in the market. But before that, there are so many hassles, so many things we have to go. And putting any graph is really a challenge. So I think so what we wanted to discuss, and we have that submissions are that really if any product has to come, it has to really go through so many clinicals, immunological and so many trials. So maybe it's a good, we are also working on the same thing, but then being a fish and being a biomaterial, it is always, good to have those. So I think so. You need more biologists in your.
No, absolutely. And see, my forte is materials design.
Yeah.
Although see, now actually this material that we have developed, both they are undergoing preclinical work in a CRO. Okay, so that is, which I am not presenting. I am not, so that wo chal raha hai. But point being that the familiarity of the clinician with an allograft human tissue versus a xenograft is very different. So although Integra's product I mentioned, it is bovine collagen. Okay. So clinician, ma'am, because ma'am, clinician is the ultimate user. आपको clinical buy-in मिलेगा नहीं ना, तो आप कोई भी कितना भी material बना लीजिए, it becomes difficult.
Yes,
Yeah, it's a practical point.
Yeah.
We all need vision, and we all should accept each other's comments and then.
Yeah, absolutely.
I think that's. I think this is the right time we have a little bit of tea now. Thank you, Dr. Adhan.
Welcome. Thank you, everyone.
Now I request Professor Ashwini Kaur to give token of appreciation to Dr. Adhan.
हाँ मास्क डाल दो।
I request Professor Anantya Bajawat to give token of appreciation to both the chairs of the session, Professor Rajiv R. Mohan and Professor Ashwini Kaur. All the participants can go for tea now. Thank you.
आगे आ जाओ। ज़्यादा टाइम
ये टी टाइम हो गया, टी टाइम हो गया, टी टाइम। हाँ, चाय का टाइम हो गया।
चाय भेज दोगे? करा बंद
Additionally, an early-stage medical devices startup founded by him is currently engaged in the development and translation of indigenous orthobiologics. He has 2 US patents and has strong ongoing research associations with the various departments at Tata Memorial Centre, Mumbai, TGIMER Chandigarh, and MS Ramaya Memorial Hospital, Bangalore. Dr. Convick's key interests lie in designing and developing biomaterial systems, processing technologies, and implantable medical devices with clinical applications in orthopedics, sport medicines, and diabetic wound healing. He has been a recipient of the Young Investigator Award by the American Society of Bone and Mineral Research.
I think your device is muted, so we're unable to hear you.
फिर जाएगा ये दिखावा
Meanwhile,
So can you hear us?
so meanwhile, when we are figuring out the modalities, I'll just introduce Professor Alan Kasik. Professor Alan Kasik is a faculty from University of Tartu and in Estonia. He's in a leadership role at his own country, and he's the director of the Center of Excellence for Translational Medicine. And recently, he's been the director of Competence Center of Disease Models and Biomedical Imaging, and also the head of Department of Pharmacology. He's worked on several projects under the EU framework and has about more than 65 scientific papers with very high citations, about 9,500. He's been an extensive speaker all across Europe and other countries, and has been awarded with the prestigious State Prize for Research in Medicine by the Estonian government. So his research is well recognized, and I would request Dr. Alan Kasik to take over and give his talk.
Can you hear me? Sorry, can you hear me now?
Yes, sir, we can hear you.
Okay. So it's completed. Just 1 second. And can you see my slide now? Can you hear me? Can you see the slide?
We can hear you, and if you can put yourself in the presentation mode.
Okay. So I can start if you will see the slides. So thank you very much. I would like to thank the organizers for inviting me and the It's really my pleasure to share our data with this audience. It is not exactly the draft development, but I hope that it will be still interesting. So, can you see the second slide now, I hope?
Yes, we do. Please go ahead.
Okay. So, it is well known that mitochondria make most of the free radicals in cell wall. In mitochondria-rich cells like in neurons, then 90% of cellular loss could be coming from mitochondria. So this loss is generated predominantly by the respiratory chain of mitochondria. And most of this loss is produced by mitochondrial superoxide that will be immediately converted to hydrogen peroxide diffusing to cytosol. And what is the main point is that the damaged mitochondria may produce much more loss than the normal healthy mitochondria. And if they produce too much loss, then they kill themselves, they depolarize, and it is also bad for the cell. And when little bit of extra loss could be beneficial, activating for the cell, an excessive loss production can damage nucleic acids, lipids, proteins, and cell. And at the end, it will cause mitochondrial depolarization, cytochrome C release, and the cell death. So mitochondria that produce too much loss are a big risk for the cell. The cell needs to eliminate this mitochondria to survive. And the only way to remove these bad mitochondria from the cell is mitophagy. And mitophagy is the selective removal of bad mitochondria by autophagy. And its purpose is to improve the mitochondrial population in cell. We remove the bad ones so the healthy ones can produce more energy and do other things. There are many pathways by which mitophagy is induced in cells. One of the best known and characterized involves the mitochondrial outer membrane kinase PINK1 and cytosolic ubiquitin ligase parking. PINK and parking. So if everything is okay, then this PINK cleaved very quickly by the mitochondrial inner membrane proteases. If it's not okay, then this PINK will become accumulated. If mitochondria depolarize, then this protease is becoming inhibited and PINK will start to accumulate throughout the membrane. And this PINK will then actually parking to mitochondria. This parking will first ubiquitinate itself, activate itself, and then it will start to ubiquitinate mitochondrial membrane protein. And this is the initial signal for the mitophagy. What's relevant is that this PINK and parking are associated with Parkinson's disease. The number of PINK1 and parking mutations leading to early onset Parkinson's disease. So, it is well known that if mitochondria depolarize, then PINK and parking pathway will be activated and these bad mitochondria will be removed. But what happens if mitochondria damage, produce a lot of loss, but are not so damaged that they are still not depolarized? Majority of these mitochondrial cells are not depolarized, even if they are not completely healthy. How could they remove these mitochondria? So the main aim of our study was to find out how the cell is removing these mitochondria that are not yet fully dead. They still have an membrane potential. They still produce much loss. So our third challenge was to find a proper model to test that. Most papers and works studying this question, they very powerful in glucose or mitochondria inhibitors that they tolerate not. And these compounds cannot be used because this is what happens to the logic. So we wanted to make the logic that moderate level of total production that is not deployed mitochondria, they're not killing mitochondria. We decided to use compound menadron. Menadron is metabolized mitochondrial complex 1 which produces unstable second phenol radical. And reverse oxidation of this is then generating superoxide radical in mitochondrial matrix, and this will be quickly converted to hydrogen peroxide and it will diffuse to cytosol. So you can see here in this figure that menadione is inducing relatively quickly the superoxide production. And in the middle you will see that it is very quickly converted to the hydrogen peroxide inside of mitochondria and it will diffuse out very quickly. And we use different fluorescent eyes and genetically encoded sensors to visualize this. And as you see, the process is fast and the peroxide level remain high for quite a long time. So we have a good model. So we decided to check that we get microphage infiltrate cells with melan. So we used two widely accepted purplish methods. Firstly, is make the pattern translation to mitochondria, which is the first step of being one pattern-dependent microphage. Because usually the pattern is just in cycles or homogeneously and it will go to the mitochondria if ink is accumulating. And you can see here that it's green, yellow patterns nicely surrounding the dying mitochondria. And in second assay we met the later step of microphagy, the damaged mitochondria engulfed by LC3 positive autophagus on membrane. So you see again in these lower panels the green LC3 signal surrounding the dying mitochondria. So the autophagosons are surrounding the dying mitochondria here. And we make quantification to see how many menadron we need to get this. So we discovered that it starts already from 10 micromolar menadron, and these lower concentrations of menadron, they don't affect the cells, they don't depolarize the mitochondria otherwise. So we decided that it is enough specific that we don't kill the mito directly, but we just induce mitophagy by average or moderate ROS production. So we had such kind of technical problem that when we worked with neurons, then we spent a month to see whether we will have mitophagy with menadron or not, and nothing really happened. So we did many experiments and then we just decided to read the manuals. And that we discovered that these supplements and media, they contain huge amount of different antioxidants. Because usually these skip life science thermo supplements, they have secret composition. Nobody tells what is inside. And they may have very different things inside. In our case it was 5 antioxidants, and of course we didn't have that oxidant response because of that. So after that we removed these antioxidants and we got of course moist mitophagy, and again at very low concentrations here. So we used also another motivated approach to produce ROS that was based on the genetically encoded photosensitizer killer ray. So we targeted this protein to mitochondrial matrix, and we irradiated few mitochondria, a little bit more than few here, with laser to produce superoxide. So you can see here the cell in upper panels, red is the normal signal, and then you have a small green area here. So you irradiated this area, and it started to produce lot of rush. And then we measure what happened after that. A few hours, or actually 1 hour after this irradiation, it started to go to this place, and these mitochondria were engulfed by IC3. You can see here triple staining, purple are normal mitochondria, green blue are rest-producing mitochondria, and the green are rest-producing mitochondria surrounded by microphagy and actin. So this was just description. We concluded that yes, moderate amount of force would reduce microphagy without killing the mitochondria. But we wanted to understand how this happens. So there are many studies showing that ROS will activate microphagy through the KIA1 NRF pathway. So this is the kind of main antioxidant pathway. If cell is okay, then NRF will be degraded by KIA complex very quickly. If there is oxidative stress, then NRF will be released, it goes to the nerve and activates genes encoding antioxidant protein, including microphagy. So we wanted to test, is that really pathway involved also in all cases? So we first overexpressed here in melanin-treated cells. So you can see that melanin induces the cotton transplantation, microphagy. If we overexpress here, we will have a nice protection, both in cases of cotton transplantation and IC3 assays. But what was strange result coming after that was that yes, it involves KIA1, but it doesn't involve NRF. If we overexpress NRF, nothing happened really, no mitophagy activating. When we made our experiments in NRF deficient methods, the effect was still there, so it was not NRF, which was strange. But then NRF doing the only substrate of KIA. That will frequent as any non-canonical rare substrate. So we tested quite a lot of work which could be very to microphagy. We discovered that one of the ECAM5, when activated or overexpressed, will do the same. It will activate strongly microphagy. So you can see here in image what happens if you overexpress ECAM5. In upper panels, you can see parking surrounding mitochondrial aggregates, and in the lower panels, you need LC3 autophagy marker surrounding the mitochondrial aggregates. So, I wanted also to be sure whether the effect of ECAM5 is KIA1 dependent. So we co-express KIA1 the billion both parking translocation and microphagy. KIA1 co-expression was not fully but partially protective. We used the other control also the ECAM5 KIA1 mutant, which is not interacting with ECAM5, something was mutated away. It behaved similarly to just to ECAM5 group, no effect. So we concluded that indeed the effect of ECAM5 what we had is fully captive, mostly captive dependent. But again, this finding was not exactly normal. So, as you can see from relatively recent review from Dr. Rita, who discovered, who discovered NRF gap interaction, even is already there, it's associated with this system. And in our paper, it's associated also a little bit with my perfect sheet. But nevertheless, we decided to go on and to understand the role of big and high in the system. What the big and high is doing, it's first updating mitochondria. It is going to mitochondria, it is still there, but what is happening after that is not so clear anymore. It is known that it might interact with care, it has interaction motive, but what happened, nobody knows exactly. So, what we saw that while there is the full-length P1 short P1 both would theoretically interact with care, only the big full interacting. You will see the IP here, the yellow bands show that there is full length present and the one is almost missing. So another thing we discovered was that the KIAP is degrading P1 that was already quite normal. So if we activate KIAP with co-express KIAP, we have much less P1 in our samples. So 2/3 are down. And it's quite relevantly that this has not happened when we co-express KIAP. It does not interact with P1. And in terms to understand where in the cells this happened, this interaction, we treated the cells with multisom inhibitor, and as you can see, this led to accumulation of P1 in cytosol, but nothing really happened in mitochondrial fraction. So this means that full-length P1 is really very progress. And in opposite experiments, we saw that knockdown of gap lead to accumulation of P1. Okay, this was now this official system. So we wanted to understand what happens if we have cross-production. And you can see again these yellow bands in the plot which is below. Yellow bands show that there is nice interaction with P1 and KIAP, and if you have a loss, then we lose it completely. And this graph here shows, the red one shows how you lose with plus you will lose the interaction. And in parallel we will have, since you don't have any accumulation, we have accumulation. The black line shows accumulation of the vegan file. The vegan file is accumulating in response of activators. So we made a lot of complex experiments with more this really the case. I will not explain them in detail very much more. So, what do we conclude at the end? We concluded that under normal conditions, the vegan file is partially degraded in cytosol by protocols, and only a fraction of fresh vegan file will go to mitochondria to do whatever is doing there. But in case of protein stress, the vegan file degradation is it accumulates a lot of mitochondria, lot of vegan file mitochondria. We started to study the mitochondria, how exactly. But without going to the ends, I can say that the mechanism was that even accumulating in mitochondria was affecting the processing of the mitophagy protein being one. Okay, what what might be most interesting here is the final question, is that we try to find a way to activate glutamine pharmacologically, to have a mitophagy inducer. So we picked up 4 different compounds that inhibit the interaction between NRF2 and CAP1 and have quite different structures. These compounds are more or less available commercially. So they molecular stimulation and what we saw is that they also directly would well inhibit the CAP1 combined interaction. We are interested here. Because of course quite expected, because this CAP1 binding mode of vegan is similar to F1. So we verified that was by more university potential. We can see in this in the presence of inhibitors, there is almost no any interaction between GAP1 and GAP5. We completely lose it. And as a result, we have a strong accumulation of vegan inhibitor. So inhibitors are really working well. And then investigate they are relatively safe in neuronal culture, whether they are will affect mitochondrial membrane, but then and except for one, we would see this, the others were okay. So we continued to work with these others until they were all nicely induced in microphage. So you see the button translator and there's the free positive dots associated with it. So effects were not super strong, but they were clear. So we also tried to use not mental inhibitors, but electrophilic GAP1 inhibitors, such as fumarate and bromelain and RAHB9. However, they were temporalized in mitochondria and were quite toxic in knockout.
Alan?
So it's my error
Alan? This is your session chair. Apologies for interrupting, but I think your presentation has evoked interest from the audience and we would like to have a few questions if you don't mind.
Okay, I just feel we want light. So that is the hours that were in clinical practice. But nobody knows exactly that what they are doing with mitochondria. What we saw here is that they are quite toxic to mitochondria in neuronal culture. Okay, just the final conclusion is that we defined the mechanism how cell would remove the rest-producing mitochondria. So this is not bad. If you want to have more details, you can see the short version between autophagy and long version of biology. What's relevant is that the autophagy activity are really quite interesting because a lot of neurodegenerative diseases are linked with weakened autophagy. So thank you. I would like to thank Pazzetti, Chauvet and Julie for this work because they made note of it. Thank you.
Right, thank you very much, Alan, for giving us an insight into the biological mechanisms and pathways, which will probably help us to deal with these diseases in a much better fashion. So the session is open for the audience to ask questions. From my colleagues or from the students who are present here.
Alan, I have a question for you, if you can see me.
Yes.
Although I don't come from a very intense biological background, but this is more of an inquisitive question or a query. So when we are dealing with all these diseases, isn't it specific to a human when we are looking for solutions? Or you can generalize in a fashion where it can be applied to a set of patients from a particular background or a particular demographic location. For example, if there's a patient who's in North America, or there's a patient who's in India or in Asia, or there's a patient from a European background. So how does it matter? How do you deal with that issue?
So it matters in some extent. If you take, for example, Parkinson's disease, then these familial versions are related with or linked with around 10 different mutations. And the prevalence of these mutations is also not so different, but is slightly different in different countries and in different areas. But in most of cases, this variation is not so big. Maybe there are few exceptions that Huntington disease has very different prevalence in different parts of the world, and multiple sclerosis has quite different prevalence. But Martins are relatively similar. I hope this answered to your question a little bit.
Yes, it did. Thank you. Thank you for that.
Thank you, Professor Alan Kasek, for the informative talk. I would now request Dr. Adnan Konvik to kindly introduce us to the second speaker of the session, Professor Ulrich Zagarius.
Hello, Ulrich, can you hear us?
I can hear you, yes.
Great. So, a quick introduction. Professor Ulrich Zachary is a professor of computational biology at the School of Life Sciences, University of Dundee, United Kingdom. He obtained his PhD in structural biophysics at the lab of Wolfgang Baumeister at the Max Planck Institute for Biochemistry in Munich, year 2004. Between 05 and 10, he worked as a postdoc with Helmut Grubmüller and Bert de Groot at Max Planck Institute for Biophysical Chemistry in Göttingen, Germany, and as a drug researcher for AstraZeneca in Alderley Park, focusing on computational and theoretical biophysics. From 2011 to 13, Ulrich was an independent super advanced fellow at the School of Physics at the University of Edinburgh, building up a team of researchers interested in membrane protein simulations. He joined the University of Dundee as reader in Physics and Life Sciences in May 2013. His research interests lie in the areas of computational biophysics and drug discovery, specifically membrane biophysics, ion channels, design of new antibacterial compounds, and flexible protein scaffolds investigated by atomistic simulations. Over to you, Professor Ulrich Zachary.
Thank you very much for your kind introduction, and thank you as well for the invitation to speak here. I hope you can hear me okay. So I'm going to present some of our work on membrane proteins, and especially focusing on the importance of membrane voltage and membrane potential, and the influence of voltage on their function. So,
Ulrich, can you please use the presentation mode?
It is presentation mode for me.
We see the slides. Yeah, the other slides on the side.
Is it better now?
It's not. It doesn't seem like full screen.
Okay. It should be. Let me just. I'll do this way.
Yeah, that's fine. Thank you.
Thank you. So, about half of the weight of biological membranes is composed of membrane proteins, and they form more than 50% of all drug targets. My group is especially interested in signaling proteins that send pick up a signal on the outside of the cell and send it into intracellular signaling pathways. But I'm not going to focus on that in the present talk. Then So another important class of membrane proteins are transporters that either transport, for example, nutrients inwards, or in the case of drug efflux pumps drugs outward, and they are normally coupled to ionic gradients across the membrane. And the third important class of membrane proteins are ion channels, and I'll start with ion channels in my talk. It is important to note that the proteins inside the membrane, so membrane proteins, are affected by their surroundings. So the membrane composition plays a role in their function and modulates their function, as well as membrane fluidity and lateral pressure, for example. But another important factor, which I just alluded to, are electrochemical gradients across the membrane. So, for example, there is a high concentration of sodium outside the cell and very little inside, whereas the inside of the cell has a lot of potassium in it and very little sodium. These electrochemical or ionic gradients, together with the existence of ion channels, create a very strong electric field across the membrane, or the membrane voltage, which is on the order of 10 to the 8 volts per meter, so it's a really strong electric field. And this is a fundamental property of biological membranes. They all have certain degrees of membrane voltage, and also this membrane voltage and the electrochemical gradients affect membrane protein function. It is obvious in the case of ion channels, but they also affect signaling proteins like GPCRs, G-protein receptors. So it is important to be able to take that into account, and the approach that we use in the group is molecular dynamic simulations, and I'm going to present to you how we model membrane voltage in our simulations. One important thing to know about membrane voltage, we're looking at the resting voltage here, is that you can distinguish proliferating cells from non-proliferating cells simply by looking at the voltage across the cell membrane. So these numbers here are measured inside the cell, so the membrane voltage of non-proliferating cells is about -60 to -90 millivolts, whereas proliferating cells, dividing cells, have a lower membrane voltage. Importantly, tumor cells, because they proliferate, share this property, and so you can distinguish tumor cells from quiescent cells simply by looking at the membrane voltage, which is an important feature of the voltage itself. An important class of cells where the role of membrane voltage is well studied are immune cells, where depolarization of membrane voltage starts the process of proliferating and activating immune cells. So non-active immune cells have a lower internal membrane voltage than the activated immune cells or lymphocytes. So let's go back to electrically excitable cells, where the role of voltage is quite well known. So excitable cells receive chemical signal by binding neurotransmitters, and then that activates ion channels, which changes their membrane potential on a very rapid time scale, starting an action potential, which is then transmitted along the length of the neuron and leads to the emittance of further neurotransmitters at the end of the neuron, and they sort of diffuse across each left, and this is the way that nerve signals are transmitted. So in all of these processes, ion channels play the major role, and as I said before, I study ion channels in the group, and if you want to really understand their function, it is important to know their structure. So protein structure normally comes from X-ray crystallography or cryo-electron microscopy in a resolution that is sufficient to recognize and see individual amino acids and individual atoms, and that is the level that we're working on. It is, however, important not just to see one state protein, which is delivered by the experimental methods, such as crystallography, but in order to understand how a protein works, you need to understand its dynamics, because frozen protein doesn't do anything. And therefore, we use simulations, molecular dynamic simulations, where all atoms in a system, for example, a protein within the membranes, are simulated individually, and they move within a potential energy. Potential energy function represents the interactions in a molecule and in different molecules and atoms. So there is a term for the chemical bonds, and bond angles and dihedrals, and then the non-bond forces are modeled as well through unannounced and interaction terms. And putting that together, you can approximate all the interactions within the molecular system, and by taking the derivative of the potential energy, we obtain forces, and these forces are then used in Newton's equations of motion in order to propagate the system. That is done using very small time steps, so it has to be done billions of times, and if you do that long enough, you can obtain microsecond to even millisecond trajectories of large macromolecular systems. And this is just a very old method the Brooks group. So in order to understand the system, now you get a lot more insight, because you can see the system move, see the dynamics. It may not be visible from this angle, but this is an aquaporin, and it was used at the time of the Brooks intuition to understand how water molecules cross the membrane selectively to aquaporins. So it's a big step forward from just looking at a static protein structure. So the molecular dynamics approach is based in fundamental physics, and alongside just looking at the dynamics of the system, it enables us to understand how the machinery of living cells works, elucidate mechanisms and underlying energetics. The simulation systems are thermodynamic systems, and so you can derive thermodynamic quantities like free energy changes or entropy, and thereby the driving forces for all biochemical reactions. And this is also important for drug design, for instance, where you can calculate the difference in free energies of binding various different drugs, for instance. What we tend to do is to use it in a sort of single molecule fashion, and one of our specialties is computational electrophysiology, and I'm going to take you through that. One limitation of simulations is the limitations are relatively short time scales. What I said, sort of microseconds. We reach into biologically relevant time scales. We cannot all biologically time scales yet. So let's look at the equivalent of single molecule electrophysiology. So the way we model electrophysiology currents is by using a bilayer system. So this is the inhibition system shown here, where the membrane is shown in yellow. The small red dots are water molecules, and the larger spheres are ions. And two ion channels can be seen immersed in the two membranes. What this double bilayer system allows us to do is to simulate ionic gradients. So because simulation systems are periodic, and they are so infinitely repeat in the computer, this double bilayer system allows us to use different ionic concentrations from the top to the bottom, and to the bottom, or from the top to the middle and the bottom again. These compartments here are actually one, so they are periodicity in this. And if you use on top of that a small ionic imbalance, then the capacitance of the membrane compares to a membrane voltage by just using a small difference in the ionic numbers in the compartments. And this is exactly how nature produces membrane voltage. It is by using electrochemical gradients and a small charge imbalance. So what arises from that is a transmembrane potential or voltage. And now we are able to simulate membrane proteins under realistic potential gradients or electrochemical gradients. And what I'm going to look at here is potassium channels. So this is the axonal part of a nerve cell of the neuron, and the electrical signal, the action potential, is transmitted by the orchestrated opening and closing of ion channels that are selected for sodium and potassium. You can see the action potential here, which sends the membrane voltage from -60 to +40 and then back. And in order to achieve a sharp signal that can be transmitted along the length of the cell, it is important that the sodium currents are completely separated from the potassium currents. So looking at the potassium channel here, you can see its general structure. The ion conduction and selectivity happens here with the so-called selectivity filter. You can see a number of ion binding sites here in the middle. And what has fascinated physiologists for many, many decades is that this channel combines super high efficiency with exquisite selectivity for potassium, which is not easy to achieve. So it requires the channel to discriminate against sodium ions which are ever smaller. So a simple size exclusion principle is not enough to explain why this channel is potassium. But at the same time, it catalyzes ion transfer with rates of 10 to the 8 ions per second, which means the channel is diffusion limited. That is, it operates at the physically maximum obtainable speed. So the textbook knowledge was taken from looking at static structures again, that ions move through the selectivity filter separated by water. So one water molecule per ion is transported. And this also comes from static view. The selectivity was explained through the fact that sodium might be smaller, but in a static structure, a static selectivity filter, sodium ions would not fill the vacancy sites as ideally as potassium does. So this is called the snug-fit model, and this is still seen in many texts. Direct ion contacts, although the crystal structures look like that, were excluded due to electrostatic considerations. So a few years back, the first open state structures of the potassium channel were obtained, and we used our methodology, computational electrophysiology, to simulate potassium permeation in the ether. As you can see, hopefully a quick movie here. All of these spheres are potassium channels. Because the channel is so efficient in permeating potassium, we can simulate each ion going through. But what you see here is that the conduction mechanism is devoid of water. So that was in disagreement with sort of the text knowledge. And at the same time, we see conduction in the right time scale and the right magnitude of conduction. So this disagrees with published work, as I said, and we therefore looked at the selectivity. So from our simulations, we got the efficiency correct with different mechanisms. But it was important to test whether we also got the selectivity right. And so we simulated the mixtures of potassium and sodium, and we obtained really good values for selectivity. So when we simulated mixtures, almost exclusively potassium was transported through the channel in anesthesia. However, we never saw water being transported at the same time. And our simulations showed that the mechanism we observed is actually required to explain why maximum efficiency is combined with this huge level of selectivity. So what we saw in our simulations, for example, was that if you think of the snug-fit model, sodium doesn't bind at all at the potassium binding sites. If it binds in the middle between the potassium binding sites. That means that it blocks conduction. So whenever sodium binds, the conduction stops, which is one basic feature of achieving selectivity. However, sodium most of the time doesn't enter the selectivity filter at all, and that is explained by the selectivity filter excluding water. So you saw in the previous movie that potassium conduction happens without water, but because the sodium ions are smaller, the hydration shell is bound more strongly, which leads to a greater dehydration panel. So in order to leverage potassium ions, you need a much lower energy than to de-wet sodium ions.
Can you hear us?
Which means that the energy to obtain naked sodium ions is much higher, and with the water shell around the smaller sodium ions, they are much bigger than the naked potassium ions. So we're and I would like to note that the mechanism we see depends on a strong repulsion between neighboring potassium ions, and that explains the efficiency of conduction. So this actually makes
could we take a pause for a second? Could we pause for a second?
Yes?
Yeah, can you hear us?
Yes?
Yeah. So if you can please wrap up within a minute or two, then we'll take questions. We'll be grateful.
Yes.
Time.
Okay.
Yeah. Thank you.
Okay. Just one last slide. As I just showed you, our simulations show that the potassium ions in the selectivity filter of the potassium channel were occupying neighboring binding sites, and we teamed up with crystallographers to find evidence for that. And indeed, the crystallographers found that it is very unlikely that water is in the selectivity filter. And a few years later, an independent group used single wavelength anomalous dispersion, X-ray diffraction, and crystal structures of another potassium channels, and clearly demonstrated that the ions in the selectivity filter of potassium channels stack up and water is not present. So I thought this was a good example for simulations informing experiments and correcting misinterpretations of experiments. I have a lot more slides, but I would like to thank the people involved in my work and the funders, and I'm very happy to take questions.
Thank you, Ulrich. So that was a lovely presentation. I think, myself not being from the area, you very lucidly and clearly explained the importance of your work. So I'll have a question towards the end, but let's start with the audience. Any questions? Any questions from the audience?
Is there any role of smart action channels? Smart action channels.
Sorry, I didn't understand.
I said, is there any role of smart action channels?
Did you say calcium channels?
Slow calcium channels.
Slow calcium channels.
Okay. Yes. I'm working. This is just part of my older work. I'm working on calcium now, and it was for molecular dynamic simulations. It has been almost possible for many years to model calcium because of its electronic characteristics. But about 2 years ago, a multi-site model for calcium has been published, and now it is possible to model calcium permeation. If I understood the question right?
Thank you.
Yes.
Any other questions?
We have a couple more questions here.
Yes, I'm happy to take it.
Good afternoon, sir. Sir, my question was, is there any other molecules in water which interacts with potassium to make their channel specific?
So, I repeat the question. Are any other molecules involved in the channel function?
Yes, sir. As potassium channels become specific because of interaction of water with potassium ions, which make them smaller molecules as compared to sodium. That's why sodium channels can't pass through potassium channels. Are there any other molecules which play a role in this?
So, I hope I got the question right. So, the potassium channels are completely selective for potassium in the body. They are highly regulated normally by lipids around them. And they can at the same time permeate non-biological ions. So, for example, potassium channels permeate thallium very well, which is toxic ion because of this reason. So, thallium imitates potassium and is then transported in and out of the cells, and that is why they are toxic. Is that an answer to your question?
Yes, sir.
Thank you.
Thank you, sir, for this wonderful session. I had a question regarding the point that you mentioned that the cell proliferation causes a change in the voltage of the cell membrane. How does this happen, and if so, in cancer cells, do we notice a dramatic increase or decrease in the voltage?
Yes. So, how does this happen? So, functionally, it is quite well understood. So, the starting point are again potassium channels, and it is known actually and published that certain forms of potassium channels are linked to cancer. Several potassium channels are seen as cancer targets. However, it is very hard to design drugs that are selective for only the channels that are involved in changing the membrane voltage in cancer cells, because potassium channels are present in all other cells as well, and making the drug selective is very hard. So the starting point for proliferation is usually an activation of a certain potassium channel, and the influx of calcium that this causes. And calcium is a general signaling agent in the cell, and then leads to many genes being activated.
I think the question was that the resting membrane potential, for example, of a cancerous cell could be different from a normal somatic cell. The electronegativity inside the cell, I think, is much more in case of a cancerous cell. And that is primarily the reason why cell-to-cell repulsion is there for the beginning of, or the onset of metastasis, metastasis.
Yes, so there are many cancer pathways, of course, and proliferating cells are not necessarily cancer cells. It's just that proliferating cells have this smaller polarization inside the cell. So whether that's a cause or an effect of being cancerous I don't know.
So Ulrich, one last question. I think we're done with most of them. It was more, from the point that you mentioned you work in design of new antibacterial compounds. So I was just wondering that when you're looking at prokaryotes, right, any bacterial species, are there strategies where you can increase the membrane permeability for certain kinds of drugs by changing the transmembrane voltage? Is that something that is being done, or is there a possibility?
Yes, so some antibacterials destroy the membrane voltage or the membrane potential in microbes. So again, this is linked, but the work I do is more. I don't know if I should share again, but just a quick overview. The work I do on permeability is more concerned about the channels that let drugs in and stopping the efflux comes from pumping the drugs out again. So the efflux is again linked to the membrane potential in the inner membrane, but here we are more looking at chemical structures that are not bound by the efflux pumps.
Thank you very much, Ulrich.
Thank you very much. Also for your questions, I hope I understood everything right. The audio is a bit difficult, but I really enjoyed it. Thank you very much.
Thank you, Professor Ulrich Lucaria, for the interesting talk. I would now invite Dr. Amit Saini to kindly present Professor Gaurav Verma and Dr. Athar Kondik, the coconut. Patiently attending the session. This session was really interesting. Now I request everyone to proceed for the tea session.
We have tea and poster session, and then we close the day one.
Poster session outside.
मेरे काम तो नहीं आएगा बट उन दादा के काम
थैंक यू वेरी मच लास्ट बार ही स्विच ऑफ कर दो हेलो